Hello. Yeah. Yes. Yeah. I think it's okay. You mean this one? Better to have this. Yeah. No, no, no. I think there's a lot of space here. Hmm? I think it's fine. Yeah. What's that? Yeah, yeah. Oh, well, yeah, yeah. Sure, sure. Shall we start or we? Yeah, I have few slides to summarize as well because some. Yeah, just to remind. Yes, few slides before opening to the topic. Sure. No problem. Hi. Want me to stand here? Okay.
You can make use of a slide changer.
Okay, sure.
You have a slide changer?
Okay.
No, the thing is the frame is fixed. So if you are moving the frame, the resolution is going up.
Okay.
If
Shall I stand here or
No. That's what.
prefer? Okay.
Yeah, you have this mic.
Sure.
I think so you are using that mic.
Okay.
You have slide changer.
Yes, yes, sure.
You can
Yes, sure.
do it from
But sometime I may need to go to place the button there. But it's okay, right?
Yeah, yeah. But not continuously. Maybe
Okay.
often you may.
Yes, sure, sure, sure.
So that is yesterday's feedback in the YouTube. I was here.
Oh, really? You can send me the link later.
Yeah,
Yeah.
sure. I will get that. So this
Um,
will be the
Like this way,
ah. Okay.
around this area. Yeah. Oh, yeah. Okay. Yes, I think we may start the lecture. So, good morning, everyone. Again, this is my next lecture on the microstructure and mechanical property modeling during additive manufacturing. And especially the process we are looking at is laser powder bed system. Laser powder bed fusion additive manufacturing. So I think just to remind what happened yesterday is that we talk about the introduction of the additive manufacturing in great detail, and then we introduce the mechanistic modeling of additive manufacturing process and identify some critical unsolved problem. today we are going to focus on the processing microstructure. And I'm highlighting here microstructure because this is the most important linkage actually from material processing and property. Microstructure is the link to tell you about what happened during the processing and what your property will be looking like. So microstructure modeling is so important, but again, as well, it's so difficult to simulate for under the rapid repeating. We're looking at the relationship between composition, structure, processing, structure, property, and then we may use modeling or experiment to investigate all that relationship. And yes, again, I mean, nowadays it's not only modeling or experiment itself can complete the picture of our understanding. So we may need more insight from the physics-based kind of simulation process to give us further insight. But at the same time, physics-based model may not be working if we don't get any additional information from experiment, targeted experimentation, such as the equation we use to simulate things are actually based on our previous knowledge from our previous experiment. But in reality, in additive manufacturing, so many things going on. And sometimes you may find some new science which is actually need to inform our model to get better representation. It's a framework we are going to take or talk to you in order to go through that in the next few days from now. And then just about emphasizing a little bit more about what I call process science and engineering of additive manufacturing. And what is that? We will know more today. And then, as I said, we will looking at more insight into what are currently available experimentation that we can use to inform our modeling for metal additive manufacturing, especially the contribution to the microstructure development during additive manufacturing. And then I will give example, which is actually just, if you remember yesterday, I did discuss about few examples, but in large, today I will try to make it slower and emphasize important aspect of the microstructure modeling in nickel-based superalloy, and then I will close the session today after that. So what is the integrated? So you will see that we have the word integrated. That means we need to integrate it some way, somehow. It's not just modeling as a modeling for its sake, no. It's actually we need to integrate it across the length scale and time scale because things happening in just short period of time. Thinking about additive, for example, powder-based fusion process, the characteristic of the process, for example, you know, we're talking about a powder-sized particle, right? It will be in the range of sometime 10, I mean, if you say traditional will be, I would say 20 to about 50 micron length scale. That is the powder particle size, if it's not larger. And then the beam size that you use, it should be around 50 micron to about 7 to 80 micron size as well. But that means if you do a simple calculation, if the beam travel around 1 meter a second or 1,000 millimeter a second, you can estimate cooling rate easily. No fancy mathematics needed, just simple estimation. And then you will see that the cooling rate will be in the range of 10 to 6 to about 10 to 7 Kelvin per centigrade. That is about the time and length scale we are talking about. Again, the characteristic length scale for this kind of process will determine by the power energy density. Depend on the process condition. This will be the size of the melt pool or melt pool geometry whatsoever. But anyway, all this information happened in such a short period time scale that I discussed with you previously. Some of you came to me yesterday and asking, what actually enough to tell just 1 millimeter domain of the melt pool? I would say yes, if you understand the characteristic is in that length scale. So if 1 millimeter is more than enough for the length scale investigated that you're looking at. So, but you can, the most important thing is how can we capture all the physical phenomena that happen during this kind of process. That is the key. And to capture it, yeah, we base on understanding from the powder particle thermal fluid, which is a kind of printing or melting, and then emerging, or we call resulting microstructure development. And these three is actually in the something that actually couple. That means you cannot consider all these individually in reality, but because things happen in one go, right? And after that, subsequently, you will get some. Oops, sorry. I think if you remember yesterday, we have some simulation, but for some reason it's disappear. Anyway, you will see that we will get to go to, again, I will call this also microstructure, because this is the precipitation kinetics, that when you want to understand solid transformation, whereas this is the place where you understand the solid liquid vapor or gas transition. This is the liquid solid transition, right? And then now this is solid transition. So it's all about some phase change actually. All these are phase change, and then you have the solid mechanics now. Once everything is solid, this one is actually going to be quite important to understand what happened and how can we simplify the model. It's not actually another way around, in my opinion, that we cannot actually underestimate what happened in the lower length scale in such a non-equilibrium, rapid repeat heating, cooling during this process. So we may need to understand from lower length scale and then bring up or simplify to the larger length scale. And that will actually ultimately will give some simple but quite capture and accurate as description of what is going on during additive. And at the end of the day, for industrial people or the end user, what they want to do or what they want to use is actually thermal signature, or we call thermal cycle, that what actually represent the process. And this is so matter because people using thermal imaging to look at hotspot in the print, and this actually then I think this is going to be the next generation of the additive, because you will collect about 10 to 20 gigapascal, sorry, not gigapascal, sorry, 10 to 20 gigabyte per layer. I'm talking about data that you're collecting in the build. Probably not too big at all, but it depends on the resolution of your camera and what is the frequency, or if it's actually 10,000 frames a second, something like that. So imagine that would be a huge data. What I'm trying to say is that if we try to get the physics-based model, multiscale, multi-physics-based model that can represent that signal, we may be able to actually do the real digital twin for the process. But again, there's so many things involved. I mean, from here to here, it's not that easy journal, actually. But we need computer science probably to make it more rapid. Physics people and also material scientists, engineer, blah, blah, blah. So this is to answer what is a manufacturability of this process at the different composition material processing condition. And then what is the key variable that we need to take into account in the printing process? Because as you may see from yesterday from the Professor Kumar talk, you'll see probably, I would say, is hundreds of variables that you can imagine in this kind of process. It's so complex, so stochastic. So this is the aim. And as I mentioned earlier, traditionally we have the technology push approach, that we push the things from what we want to know from the property, and then we inform the process that, okay, we want this property, how can we make it? Let's say in forging, casting, or standard metallurgical process, it's probably possible because everything happening in a near equilibrium condition. Whereas the additive, we may need to understand from the processing side what happened during the process and what the process doing actually, in order to tell you a little bit more about emerging microstructure. Again, I will emphasize more the microstructure part, what happened of the process to the microstructure, and this structure will inform you about the property which will happen after that. And again, and this one is sign push. That's what I said yesterday. So again, this is all about modeling now, nothing related to very fundamental understanding like yesterday. So please let me know or pause me anytime that you have any question during the lecture today. So all of this is just about the relationship between composition, process, structure, property. Again, if we are talking today some, yesterday a bit large, I know that I'm talking about composition here. This is all nickel-based superalloy. Some of you are interested in nickel-based superalloy, and then we will have some example today, more example for nickel-based superalloy, especially the legacy alloy, or we call existing alloy, and the new nickel-based superalloy as well. So again, the tools that I'm going to use, definitely this is all about model. It's all about computational. It's actually, we have the, previously my project related to alloy by design framework, that you use alloy, a computational framework to come up with a new composition. So we use a lot of data from literature database or database from thermal calculation, calculation or thermodynamic calculation. And after that, you need to bring this new powder or existing powder to process in the different process variable. I mean, this is just a highlight, but in reality, it's much more than that. And probably for ML or machine learning model, we may need to define how many variables as an input for the model and which one is actually important. So again, I'm not going to talk now, but just try to emphasize this. And what is the process condition you are talking about? It's just what I am going to talk in this lecture will be as fabricated or as printed, and sometimes a little bit on heat treatment and heaping. So we'll be doing the processing and then post-processing. So there are several tools that we use to simulate in this process step. So we probably use the kind of process simulation using CFD, which is computational fluid dynamics. So the fluid we're talking about metal fluid dynamics during the process, because this is a melting-driven process. It's not sintering. That is like diffusion-driven. This is melting-driven. So it's a lot of melting. And then once actually just solidify before the transition of solid to liquid to solid, you may want to use, or doing this liquid behavior, you may want to couple as well with the thermodynamic property, for example, liquid property. And the structure is a lot. If you are experimental based people, I mean in mechanical or material engineering, you may want to know the defects content in the process, like porosity, whatsoever, how can we differentiate this process-induced porosity and the lack of fusion porosity. And the porosity can come from different sources, like porosity trap during the atomization. How can we differentiate that from the process-induced and also lack of fusion? You see, the origin of these are all different, but I think what the matter to the end user is what really tap inside after this, because this, as a mechanical engineering guy, you may want to know, because you want to know the failure of this part if there's some content. But without predictive capability from this processing simulation or process simulation, you won't be able to predict anything after that. If it's just a speculation, it's not possible. Or another way is to do some experiment, extensive experiment, to get this information, and then using a kind of finite element framework to calculate what is a criteria for the failure, for example, opacity, whatsoever. There's some other phenomenon that you may not be able to do or derive easily from a simple model like surface roughness. So because you need a interface capture approach to understand the change of the interface in order to predict what is a roughness. Again, this is all about interface tracking. And then grain morphology is a subsequent phenomenon that happen after things solidify. So we're talking about now about liquid to solid transition, or so you will get to see the grain growth or coarsening or whatsoever under this condition. And then some of the research going on in the texture control, that means not only the grain morphology, but about the grain orientation. That probably matter in the property later as well. As a crystal plasticity people, that you calculate the orientation dependence of the material. This may actually induce some different specific property for some specific location, which is sometimes we don't want to homogenize everything, constant property, but the life is not easy like that in AM, in additive. Another thing is about you may not only have single phase, you may have secondary, tertiary phase, which is present during the process. Some of the phases which is very detrimental, for example, brittle phase in the Inconel 718, you may get the Laurus phase, which is actually brittle phase. If it's decorated at the grain boundary, that will harmful for the life of the material. That will create some crack, right? It will be intragranular cracking during the process. So that's not preferable. We need to understand where this happened and how can we remove that, avoid that if all possible. Segregation is another thing which is actually we found recently is a prominent effect. For example, there are some study, both experiment and computational approach, to understand some effect of the segregation of some certain element that may be able to help the process. So it's still under investigation at the moment. For example, there are research published in the non-weldable material, but they try to improve this one using some boron content into it, and then they believe that the boron will segregate into some dislocation structure, blah, 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 and then you can, that is the reason why it's not possible to get this composition printed under the very severe cooling, heating condition, for example. So this all understanding will contribute to the model development anyway. Crack is another issue. So many, when you say crack, it's quite different from different people. So I may talk about carbide cracking, like I said earlier, ductility dip during the process. So if you not control the cooling or heating profile during your post-treatment, this may induce some failure as well. Solidification cracking is much related to the process. So we'll link back to this process. So, and then resulting of this, I mean, all this one integrated will reduce, contribute to residual stress and distortion. So a number of ways you can use, optical microscope, high resolution scanning electron microscope, high resolution EBSD, combined with some Python scripting, MATLAB coding, analysis whatsoever, so to understand these things. And then last but not least, at the end of the day, as a people in mechanical or material engineering, so we want to know the mechanical property, right? Either time dependent and time independent property, but especially very important if you're talking about the aerospace application or the biomedical application. Most of the time, our concern is time dependent property, like fatigue, because it's rotating part, you will get subject to this fatigue loading. And how can we go about it? Everyone will ask me, how can I predict crack? And then fatigue, and then you simply forget all complexity before what happened like that. So that's why I said all this contribute to the final property prediction. But I appreciate that someone will focus the research, the group working purely on this, on very comprehensive research on this, or purely on this, that's fine. So the way we do, we're focusing on this processing simulation, we will collaborate with them. So I take quite a long time to recap what happened yesterday, and just want to give you a big shot of what actually we anticipated and what is meant by multi-scale, multi-physics simulation. That's what I use at the cover slide. So on the top row here is a kind of experimental work, but nowadays with the rapid calculation, even quantum computing that we are going to have. We are not going to talk about the past, we're talking about the future ahead. So you will see that we have so many ways to storage the data, computing smaller but faster. So this one is, I mean, for example, this is, I think it's supposed to be high resolution TM. And then you will see a kind of atomic arrangement of the particle. You may be able to use this to validate your model in the first principle calculation or molecular dynamics simulation, for example. And nowadays, more and more, we found that there's a lot of in situ hot stage transmission electron microscope that can understand what happened, the dislocation dynamics during the process, and you see something looping or cutting through something, which is actually there is another group of the world, I mean probably in the States or in India, looking at dislocation dynamics, and then you can see some kind of dislocation pattern. Again, this is relevant to mechanical engineer as well. So you may use discrete dislocation dynamics. Again, I'm not going to talk about this here, but to be honest, there's some interesting research going on the we call Sarah structure development during additive manufacturing. So they have someone already published the work in this area under condition of additive. But what we are going to focus today is this bit. But because yesterday we talked about it. Today we talk about microstructure. So microstructure means differently. So microstructure itself is hierarchical in the additive manufacturing process. So it doesn't simply mean just grain size, but probably content segregation inside the grain of microstructure cover the, I mean, how to say, I mean, equiax, columnar transition, something like that as well. So this hierarchical microstructure, we were looking at using probably phase field approach or statistical approach like Monte Carlo calculation. Or for example, what we use Sarah-Tomatin finite element method or CAFEM. So this one can validate again the high resolution SEM or STEM, which is scanning transmission electron microscope, that you can see the detailed morphology of the microstructure of your interest. And this can, again, this is also interface captured technique that we use phase field here. And then we can actually translate across here. I mean, this and this one are different length scale. You will see it's about 3 orders of magnitude different in terms of the length scale here. And then, again, when they say microstructure, I will ask the guy, what do you mean by microstructure, actually? And then after this, you will get the kind of, I mean, the overview of what happened in the larger length scale of microstructure. I mean, all this scale we call mesoscale simulation. Yeah. So this one you get the grain structure, columnar equiax, or where is it? What is the inference of the scanning pattern to this microstructure? A lot of people around the world, especially the pioneer at Sandia National Lab in US, has been done, and I'm sure there's some group in India as well. What I showed you yesterday is about, okay, the scale now is a bit larger. So we use high-speed imaging. But I actually want to write more than this, because this day, I mean, our camera is so good, better and better. So we have so many variety of camera, I mean, lab-based as well as a national facility-based camera. What I mean national facility-based camera, I'm talking about synchrotron, neutron diffraction, that you can see something very small scale, but very precise and then detailed dynamics. And that include in this as well. So we're looking at in this mesoscale area. So this is a mel pool. And this is very, I would say, old. At this day, we're talking about, if actually more than 10 years is about old now. The new things we need to talk about 3 years from now. I mean, in this age. It's not my own time here. So we did this since 2013, 12, 13. So it's very old. Here we use quite good camera at that time. And then we can capture what happened doing a dynamics there briefly. we do some image analysis as well to look at the dynamics. If you have any question about this, I think probably it's worth revisit the yesterday talk more on this. But today, what I will not capture. So this one will be more about fluid dynamics calculation. And then after that, you will interested in, I think, as a mechanical engineer, you want to do diffractometry, probably not, I mean, in the light source elsewhere to understand the residual stress, I mean, or distortion, or use laser or whatsoever you have. And then property testing, this is the length scale we are talking about. But this one will have the contribution from the lower length scale like this. So you will see this is an example of the nickel-based superalloy printing here. You will see I mean, this is not gamma prime, this is probably gamma double prime, sorry. I'm missing double prime here in an inclination 1/8. Because inclination 1/8 is gamma double prime strengthening material. So this is the matter. So we want to know how this gamma double prime distribute along the way here. But in traditional process, we don't really much concerned about this because the microstructure is quite uniform. But for additive, it's not like that. You get a wavelength of the microstructure across your component, which is of concern, and need to take care of it very carefully. So this is actually, we may use several finite element technique, crystal plasticity, or sometime with the precipitation here, you use mean field approach. Anyway, it's just a highlight summary before we go into the real things. So what we do in this kind of length scale, just to remind again, is actually just solve four equation at least. If it's not 5 or 6, I mean, yesterday I talked about probably 5 sets of equation. But here we solve about continuity equation, mass conservation, momentum or velocity equation. And this is a Navier-Stokes equation, basically. And this is the energy conservation based on the second law of thermodynamics. And then we may identify the heat sources actually used. Again, this is a more simplified version that enough for you to capture the liquid fluid vapor transition during additive manufacturing. That is a very first paper that I'm introduced as well in 2015 or so. So, yes, I think probably now this is all about modeling, and then we want to get more insight into the process of it a little bit. Again, this is still similar to yesterday, but just want to capture again after we revisit all the modeling tools we have. So this is what actually happened. As I said, this image or this high-speed imaging has done in 2013, or if not before. So we see a lot of detailed dynamics, and this is an inspiration for me to simulate it using the CFD calculation. So you will see that my point of this is that I would say I have experiment to inspire my modeling. It's not just not like for the sake of modeling, I do modeling. But I see something going on here, and then you see a plume of the vapor. And a lot of work now. Trust me, if you can go to Science and Nature journal, you will see a lot of work talking about sputter, about the melt pool dynamics during 3D printing. And this is actually just coming up about 2018 onward. But we are looking at 5 years before that. And then solidification structure, this is also important, and thermal response. Today we will focus more on this solidification. I think I'm talking too much this beginning. But anyway, yesterday we have summarized the diagram of what I discussed previously. I summarized in this schematic diagram, and then we will focusing on the thermal fluid dynamics part here. Again, this experiment also inspire me to do some process simulation. So stochastic nature, we may have some variation of the process parameter like layer thickness or scanning speed. These also contribute to the surface finish of the build. So this will be actually, if you use quite, how to say, thin layer thickness, you may get better quality of the surface finish rather than using large print. Several reasons, but you can find more information from this actor paper, which is quite good citation here. And then when you scan it slowly, I'm not saying slow, 2.0 meters a second is not slow anymore, but this is the good things for powder-based fusion process, that you can scan fabricate it very fast. And then if we double, almost double the scanning speed, not double, actually 25% increase, you will get worse surface finish, for example. And then if you talk about porosity, we show in the titanium 6.4 as well that there's some correlation with the layer thickness here. If you do it with care, you will get quite minimum porosity, but if not, you get a cheese-like structure, very porous structure, which is not good to fly this material on plane. And the scanning speed also has some relation, but not completely. When you go to the critical number here, you will see some trend up until about 3 meters a second, but after that, there's something happening going on. So again, this is actually open for further discussion. So another possible reason is that the melting mode changed from conduction to keyhole mode, and the dynamics there actually changing as well. Vaporization may take place, or blah, 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 for example. And today, just want to emphasize that we are going to talk about liquid-solid transition. I will skip all other part now. It's been too long in here. So, and microstructure for me is mean liquid-solid transition and also solid-solid transition. Again, this is a new part. Sorry, taking some time to review what happened yesterday. So what is the microstructure modeling? How can we use experiment to inform our modeling, actually? So I'm start looking at from bigger picture, quite large view. So you see side view here. This is a high-speed camera looking at side view. You will see some particle flying away. And then from the top view, you see some sputter, melt jet, or whatsoever. And if you look at from the side view, oh my God, what happened actually in here? This is we call the fluid particle dynamics. So you will see a kind of plume of the powder particle and mixed with the vapor here. And this is there's a convection flow, some entrainment of some particular vapor in the steel 316L here. And then you will see that it's turbulence flow. So the assumption made previously about laminar flow may not be possible for the liquid fluid particle dynamics. Again, this is an example that I'm saying to you that, okay, this is another view for multi-tracks. This is not reality, like this is one track, but if you use multi-track, multi-scan, what happened? But what I want to say here is this. So if you have very high resolution camera, you can actually basically say what happened during this printing. And this is not actually something we can ignore. We have to take a spatial care of this. What happened in this is actually, we're talking now different simulation set. So this is a different matter. So this is actually between something we're not interested in for material people. Material people what's interested in what happened to material that you build. But this one may contribute to that material what you build. But what we do here, we may collaborate with someone in the full dynamic guide to understand what happened here, because this plume of vapor will contribute significantly to the laser absorptivity. For example, if your laser actually downward here, in the vertical direction here, you will lose a lot of energy due to this plume that's actually coming out. So you need to find a way to remove this when you print the next layer, for example. So if you think like this, so I think now what you've seen from experiment is quite inspired to model, first of all. Secondly, inspired to change the practice in the printing during the additive. Again, this work actually old work already. I would say 5 years. As I said, I define new as a 3 years. Another unpublished work is actually inside again in we call thermofluid particle dynamics. So you will see both. This is the thermal imaging estimate from emissivity of the high-speed camera. Yeah, you will see what is going on in the melt pool. So this melt pool is not just a melt, but there is a mixture of liquid and also solid particle as well. So you see here there's some bubble. Probably some of you asked me yesterday, we not only have the transition from liquid to vapor or solid, we may have solid to vapor, and at the same time we can have backward. Well, in another term, we can have vaporization, or probably we have sublimation, or we have condensation back. Again, all these interfacial phenomena are also needed to taking care of. You see now a lot of things going on here. And how can we model it? How can we represent this reality? This is the question, actually. And then I'm not saying something new. It's actually quite old work that they use high-speed imaging combination combined with some detailed image and data analysis. You can identify what I talked to you before, like a vapor zone. So there's a plume gas here. I will show you the a kind of moving simulation later. But if you go into this paper, this is a very highly cited paper by my good friends at Imperial College London, that they're looking at the detailed dynamics of this just melt pool but in additive condition. You will see that it's more complicated than just assuming that the melt pool is static, a steady state, and you use live welding. It's not perfect like that, actually. Live is much more complicated here. And then I showed you yesterday that we can implement some kind of physics-based model to predict the dependency of the alloy composition to the printability of the material. But this is what I want to show you. So this one will contribute to the, you see now, it's just focusing on one melt pool. And you will see the temperature go above 4,000 centigrade, and then you see something coming out here. At the same time, if you vary the process condition, this is extreme condition here, you see. And how can we simulate it? How can we represent this reality? This is the question. And if you see all this, you will notice that nothing symmetry. Nothing can assume just single perfect envelope of melt pool and then passing to a part is not reality. How can we make it more representative? This is the question. Because this information may be important later to the, what happened? May be important that you will know, because this thermal cycle that I showed you before, this will be contribute to, if we draw something that make relevant to the microstructure now, you will know the vapor, or we call boiling temperature, or vaporization temperature, liquid dust temperature if it's alloyed material, and then you have liquid dust and solid dust temperature, and then you have all the secondary phase, we call solvent temperature, when it's actually start to form. So this line may have 5, 6, 7, 8 whatsoever. It depends on the material system you are investigated. But again, you see this thermal cycle actually go back and forth. That means it's coming out, dissolve, and coming out again and dissolve again. It's not simple like a smooth thermal cycle that we used to simulate in casting, forging, or whatsoever machining process that you used before. They have very simple thermal cycle to deal with. Just give you an example and then try to answer one of your questions yesterday about what is the matter of the particle packing and particle morphology to the thermal cycle. This is a good calculation and example to show that with I think they also vary the surface morphology as well. When I mean by that is elongated powder or perfect spherical or satellite irregular. Again, it depends on the calculation domain you have. you see here that with the looser packing density or smaller packing density and larger packing density, you have different thermal cycle, just one cycle. I mean, I'm talking about first one here. You will see these two differences are prominent in the build. It's just one single cycle. It's not going to melt or remelt again, but you will see these two cases. It contribute to this significantly, and the peak temperature here tell us a lot during the how to say property or microstructure prediction. I think I don't need to emphasize how important of this thermal cycle to your crystal plasticity FEM simulation. Again, this is another example that we use microstructure simulation, but microstructure in the sense of from process to microstructure. This is a phase field approach that they apply to titanium 6 soil. I think that's what we inspired yesterday. So they have some set of experiment and try to simulate the processing map. In this one, this is purely computational. And then you can replicate kind of key feature in experiment. But again, this is just 2D simulation, but it's probably good enough for industry to use. And this is the calculation and also experiment that they validate. So it's quite good. With the physics-based model, you can actually capture some of this. Again, the calculation time and resources are needed to make this happen. It's not simple. Trust me, as it looks here. Another things that we talking about experiment inform microstructure. We know that the scanning pattern is so matter to the final crack initiation. You will see here, different scanning pattern here may reduce the occurrence of the cracking, actually. So again, this is not traditional scanning pattern, but you will see this is a way they define as a non-weldable nickel-based superalloy, CM247LC. So you will see that changing the scan pattern is help a little bit, but not completely. But they suggest that we need to take care of everything in additive. Scanning pattern actually will tell you about how the thermal actually signature in your printing. Next one, again, this is much more about processing. Processing can help, how to say, homogenize the structure that I showed you at the beginning. This is Incana 625. You see there is a few heat treatment protocol that's been taken. I mean, again, this selection of temperature here based upon the understanding from thermodynamic of the phase, which is actually formed or dissolved after some time. When you precipitate out, heat treatment at 870, heat treatment at 980, and heat treatment at 1150 produce different microstructure. It's not like a previous known process. It's quite stunning that things can change even completely after printing, actually. So one of the idea of my research is how can we get one motto in what we are doing, or what we're trying to do is actually print, solve, harden later. Print, solve means solve, no hard phase during printing, but you precipitate out some hard phase to strengthen the material later. But that means you will need to know specifically. I will show some example, which is actually I shown yesterday, but I didn't emphasize. So we print solve in the solid solution manner. Even this is a quite decent size of the how to say secondary phase component, but we know that during additive manufacturing, there's no secondary phase present. And then we print solve, and then we bring out harden or precipitate something out later. Again, this is not easy as I said, but it can happen if you understand the process well. Another example is 316. You see, this is really hierarchical microstructure from I mean, high resolution chemical imaging published in Nature Material. Again, it's quite old now, so you can vary the property of this microstructure quite significantly, actually 3 times of yield strength. You can design. So additive sometimes is so amazing that can offer many, change in the properties like this. So if you can find some property that change dramatically like this, it's probably going to high impact journal easily. Like I think Professor Kurumar showed me quite impressive that he can use the metamaterial design or lattice design to actually lower the stiffness of the titanium 6 ore from about 100 gigapascal to 1 gigapascal. So this is something interesting. Sorry, I'm saying stiffness here. And then what is a microstructure simulation now? Once we inspired by this, so I want to start from some example that probably attract more of your attention. So I think a little bit similar but not the same, but I think it's good representation. It's actually, anyone here know laser cladding? It's about feeling the material. It's about laser matter interaction as well. I would say it's a kind of additive somehow. So we use this nozzle and then we add some material, and also we weld it, or we fill it. Sorry, we fill it, and then this one is cladding means probably like this, just filling the material in a specific location carefully. So cladding is actually kind of high quality welding, I would say. Or even we can say additive as well. But this is the simplest form that I would like to show you about microstructure modeling. And small heat affected zone, that means the zone that affected by the heat is small. And then small thermal deformation, a good bonding performance of the repair at the substrate. And this one basically using for something like we want to repair and overhaul some part. But I mean, this is a pipe, I think, and this is stainless steel with low surface hardness. And then these work pieces actually may result into, there's a wear here. If you some typology, if you're working on this area, might be interested in, find some real interest now. I mean, for me, physics is the same. I will say you later. So what we do in this specific case of microstructure modeling here, we want to actually kind of repair this part. Probably you're thinking about repair of something using additive manufacturing, but this specific process is called cladding. And then you want, because I tell you previously that this addition of the material in a specific location, that may be the weakest part of your component. So you need to strengthen somehow, some way, right, to make it actually usable after after service here. You can go back and then put this steel type back. So we propose to use some nano reinforcement particle. So this is tungsten carbide to actually change the microstructure rather than like a columnar grain. If you remember yesterday, we want to break this structure to be egress. According to patch hole equation, you may actually increase the strength of the part, something like that. So this is what we do. Different size of tungsten carbide here, 10%, 20%, 30%, and 40%. This will change the microstructure. Again, it's informed by experiment somehow. So the different size, content, and distribution of tungsten carbide here result in uneven distribution of element in the cladding layer. It's basically it's an adding like additive. So in microstructure distribution here. So different content here, you see there are two things need to be added now. Dynamics of this tungsten carbide. Tungsten is an extremely high melting point temperature. It's about 3,000 degrees centigrade. And then probably this laser may not go that high if you use quite low energy density, enough to weld this steel part, because the steel melting point is about 1,600 or to 1,500 to 600 centigrade, right? So you just melt the steel, but not. Particle is hardly melt, so this will be there after service, after fabrication. So how can we actually take effect of this size of particle fluid flow here to resulting in microstructure, and then we try to change the mechanical property, not just with and without this reinforcement phase. So addition of reinforcement phase has a significant impact on the certification structure or microstructure and property. But the mechanism of this is not clear. Actually, this concept also inspired my current research on what we are doing in the microstructure modeling as well. I will show you. So that's me. In order to actually the case number 1, we define the microstructure evolution model. So we use the Celta Automata finite element framework here. We have some particle which is distributed here. This is the mesh size, 1.1 micrometer, not millimeter, micrometer. And then in the number of calculation domain here, we have 40,000 elements here. So we have the tungsten carbide like distribution like this at time 0. Again, we solve 4 equations. I think we missed one equation, which is, I think, conservation of mass, conservation of momentum, which is Navier-Stokes equation, species conservation, because you want to actually capture what the detailed microstructure or segregation profile. And then last but not least, you have the, I think this is energy or enthalpy conservation, H meaning the change of the temperature as well. So enthalpy change due to weld fusion or enthalpy change due to the evaporation, for example. So what we can see here is that if you're looking at different locations, as I said before, again, we have this tungsten carbide decorated here. At different locations, you get different kind of microstructure. When I say here, at the top of the layer, we will get this kind of ecrax grain because the dendrite behaving like this. And if you go to the bottom of the cladding layer, you will get this kind of columnar, columnar grain structure here. Again, this is quite interesting about the interaction of this dendritic growth with the dendrite here, because this actually pin some grain boundary. I think as a mechanical engineer, if you're doing some mechanical simulation, this will give you insight into the origin of what happened. But this is just the beginning. Next step, case number 2, okay, we know now this particle has an impact at different locations of the build. Let's say if it's in 3D printing. The next understanding is about what if we increase the domain size to something quite representative. So 20 millimeter, not like 200 micron like before. And then we have a thickness, the height is 10 millimeter. And then we have the substrate. Again, this is something need to be informed by experiment. What is the initial microstructure that we need to simulate? This one is actually I can't remember, I think it's probably 30 micron grain size here as a substrate, because steel. Again, this depends on, this is 316 and 304, sorry. Again, you will see that this is calculation domain. We solve again those 3 equations. Oh, sorry, not 3 equations, just 3 conservation equation, 4, sorry. And now we change a little bit. Again, you will see the numerical approach changing now from only Celta Automata will change to the Euler multi-phase flow model with Celta Automata. Basically, it's the thermal fluid flow and then microstructure, because we want to couple these things. And this is the result. This is the experimental result. Again, this is 316, sorry, not 304, 316, and this is the robot we use for the 2 kilowatt semiconductor laser here. And this is a property of laser cladding. Again, you will see it's not too much different from additive, but just to give you a clear example with the validation that we have, you will see the cladding layer here is about 75 to 150 micron layer. And then the different location have different microstructure detail. And then if you, at the lower and at the surface, I think, surface and the lower area has different characteristics based on the distribution of this tungsten carbide as an initial condition. So what we do with our particle, we just run the, I would say this is not very detailed fluid flow, but you will see that this is actually added the material here, and this is will follow the thermal, I mean, you will see some addition of the material here, and this is what happened. This is a fraction of liquid, I think, at of 0.5. So you can identify the melt pool boundary here. And the distribution of temperature at the first step is actually about 2000 Kelvin, which is a little bit above the melting point, about 200 Kelvin above the melting point. So the maximum temperature of this melt pool increased sharply, then decreased, and gradually increase and tend to stabilize at about 2000 centigrade. So this is microstructure now, and we want to validate what happened in experiment. So the height and the depth has been characterized. Again, we not capturing this quite well, but I will tell you more later about it. Is that, but error between simulation and modeling is about 6 to 6.5%. It's actually not too bad, not a bad representation of what happened, because we want to validate this thermal model first before we use the grain growth simulation here. So this is what we simulate later. The grain growth along the certain angle with the laser scanning direction will behave like epitaxial growth, or we call columnar grain, which is growth here, and the formation of the new grain. And phenomenon is similar to existing research result, because, again, just to let you know, this is no tungsten carbide. It's just thermal model, because we need to verify the model first. That's what we do all the time, even in a very small scale calculation. But this is the cases that we run for validation. Again, this is quite large domain, not small. This is about 20 millimeter. But again, we will have to reduce the size of this when we have detailed information kicking in and coming in. So now we have particle. Again, different, apart from, I think, but don't scare about this, because tomorrow one of my postdocs will give some lab session on this, but probably in different cases. We will show you some fluent software, how we set this up. Again, once we introduce the particle, things more complicated, because you have interface, you have fluid, and you have solid. And this solid is actually another phase. You will see how many phases present in your calculation now. So you have fluid, solid, they have interface, you have tungsten carbide, you have the interface of that, and you have the air, which contribute to. So it's so many phases. So again, we combine the Serra automata, which is microstructure prediction, and the Euler multiphase flow algorithm. Rather than two-phase problem, it's multiphase flow now. Again, it depends on the definition of your problem at the beginning, what you want to know. So what we do is we try to capture what happened. Again, this is just a phase fraction. You will see that the small particle here is a tungsten carbide at the interface or whatsoever. And then you can see the interface here later will represent the fluid flow, because some of the recent experiment in synchrotron, they use tungsten as a particle tracer to understand the melt flow pattern inside the melt pool as well. So anyway, because of high melting point. So what we do, we have to validate again. Because with particle, we also doing the similar thing, but now with particle, but run only, just focus on thermal model. And then you will see that compared with the absence of the tungsten carbide, the temperature field evolution after adding tungsten carbide is look similar with or without just temperature field. But the Y in 3-stage or maximum temperature of the stable melt pool is about 2000. It's reduced a little bit. It's just below 2000. I think this is probably you can explain, right? With and without, with tungsten carbide, a little bit lower. Just not too much. Actually, this one is just about 10 degrees centigrade, 10, 20 degrees centigrade. And this is much more interesting. So again, we validate again. So we compare with tungsten carbide, we compare this with the real experiment. And this is the error of the melting height here of simulation and the experiment is about 5.2%. Again, it's not really accurate, I would say, from our definition, but it's actually working. It's working under condition investigated. But we have to compromise a little bit. If we couple everything, it's too expensive calculation. And then we now try to look at EBSD result, adding tungsten carbide here at this particular location. Compare with the result here, you will see the mesh size here is quite coarse. That's because our calculation domain is large. If you want it high resolution, you need to reduce the size and increase the mesh size, the resolution. So due to this 30 micron of this layer here, so the columnar grains going along the thermal gradient direction when we pass to this tungsten carbide region. And there is no competitive growth of the columnar grain on top of the melt pool. And E-crack grain can further growth here. This is the way, how to say, solidification pathway that you need to understand to. Say again? A cladding, we can assume single layer, yeah. Let's see. Wait a minute, yeah. Let's see something, yeah. So now we want to have overlapping process. That means you may need to fry away actually to make it more, how to say. So this one, again, we in the melting model, we want to have the volume average method coupled with the oily and multi-phase solver here. What we mean by that is this. I think I'm trying to answer you when we want to do multi-layer or deposit more than this, what happened? But you need to bear with me a second, because when you adding this was just tungsten carbide, but now we want to understand the distribution of the chromium. So this is another layer of microstructure information you want to see from this kind of simulation, which is not easily traced by experiment. So what we do, we have some domain calculation strategy, like we have this is the same as, I would say the same as 3D printing somehow. You have different scanning pattern. So you scanning the same direction overlap. That means you add another track on that, or you reverse the direction of overlap. What happened to the microstructure with the presence of tungsten carbide and with the focus on the chromium distribution field? Because I don't need to emphasize who working in steel here. You will know is how important of this into the property later, right? So this is what happened. So we verify again every time we introduce the new, because the modeling framework changed as well. If you notice, we are trying to highlight in red here. So again, you may think this is the same, but not. We need to change the calculation framework or modeling framework to capture what we need to know, right? So this is actually melt pool verification, a 3D as well from a high-speed imaging, compared with the modeling here. Again, we get approximately the same kind of accuracy in the under condition investigated. But for the height, we have quite small error, 2.5%. But for the depth, we actually probably something we need to take care of is 6%. But in another cases, we get about 6 to 8% error. But if you are compare this with high-speed imaging on the top view here, there will be some error about 10% when you have the overlapping region. I mean, this one purely on the emissivity from the and the contrast on the high-speed imaging that we calculate the differences between the Melpool dimension of the model and the experiment here. And this is what we found. The overlap, let's say, you can say overlap is a hash spacing. Hash spacing. So if you overlap by 50%, 45%, 40% overlap, there are some differences. I mean, again, this is a I think this is now, they deposit more layer as well. So this is quite real representation. Then we take the verification using EDS across the area. I mean, this is a section we take the error experiment and modeling, compare in cross-sectional area and longitudinal area. So you will see that the model somehow, some way, quite good agreement with experiment, not only by comparing this experimental result with the Melpool dimension mentioned earlier, but also with the Mel flow rate. Again, in the Mel flow rate, if we have some particle which is already there, and then we use some imaging analysis, we can track that particle by imaging analysis, and then we can deduce some fluid flow, velocity field. Every information will be coming out almost automatically, and then we use that to validate with our model as well. So it's not just a fancy number, okay, 10 meters a second. How come 10 meters is actually so much already? So we use, it's quite good agreement, as you see here. I think we don't have time to go into such a great detail, but what I want to say is that the prediction of distribution of chromium also verified by EDS as well. So this is what is happened. And then just try to summarize in 316 steel substrate here. So if you compare the fluid flow, I mean, I would say hash spacing, and it's in the same direction. We take into account of scanning pattern to scan in this direction. You will see that the maximum velocity of Melpool increased 15.4%. But what is mean by 15.4% here? So this is what happened. So overlap, you will see. That means there will be some region. If you see about, this is a multi-track, right? Multi-track hash spacing. So this overlapping zone will remelt the material here. Fluid flow kicks in, and then what happened? But another layer of complication that you have tungsten particle as well. And this has been compared with different hashing spacing, hash spacing. Again, this has been done already. Verification with model, with experiment, detailed experiment, high-speed imaging, EBSD, EDS. Just give you a flavor example. What is the use of our model, actually? So modeling in additive is not just for the sake of model, but it's have some useful, provide additional information that experiment cannot be done directly, for example. So up to here, do you have any question before we, yes, please. In this case, yes. In this case, yes. Yeah, because it's probably bring the particle, most of them to the top layer, as we show in the case one. But if you have a lot of powder particle, this will break the columnar structure. So from epitaxial growth will be equax grain at the top layer. That's what your question, right? single layer yet. But later we will have more layer. Yeah. Yes. Yeah. Floating on top. Yeah. That's equax grain. Yeah. I think because of the what we done for another work is actually we found that the flow pattern actually bring this heavy particle upward. It's about the flow dynamics and condition that you use. Let's say if you use quite high energy, this may promote more dynamics of the melt pool to floating things around. And then because this process is actually rapid heating and cooling, it will freeze the structure up there. And having said that, it's actually there's some particle at the bottom as well, but it's lesser. As I show you at the case one, if you remember, a lot of tungsten carbide will induce the equax grain, and then the lower will be columnar. Yes. So I mean, this is that means we as a modeling people, we need to understand the experiment very well, what happened there. Otherwise, we cannot represent what happened in the model. Sorry. Yeah, that's right. So if we don't understand experiment very well, we cannot produce a model to give extra information, because this is the benefit of the model. We will provide extra information that your experiment cannot measure. And probably suggest, add on top of that, we suggest further advice about how to improve it, or how can we just next step here. If you like, if this is an industrial project, which is it it is an industrial project, what we do next, we change the condition, and then we see how can we improve that, and that's it. Right? That's what sponsor need, right? That is the point. Yeah. So having said that, just want to make the point here before we moving a little bit to the next lecture on the mechanical property prediction. Just simple, without any detailed microstructure, we cannot integrate or simplify the problem, because as you see, the example I show you, which you will see more example tomorrow, probably 3 or 4 from my postdoc with Joy Online. I will joyfully present with him next tomorrow. You will see that without detailed information, you may not be able to deduce any analytical approach correctly or represent enough of the process, and hence the data-driven or reduced order model probably almost impossible to capture what happened in the complex scenario in additive manufacturing. This is one thing. Yeah.
Nucleation starts from, in one case, nucleation starts from the substrate itself, while in the other case, nucleation, there are variety of nucleation sites. And why not the nucleation sites are itself from the surface of the tungsten carbide particle?
Okay. This is good question about nucleation, but at the moment, what we did, we assume kind of a uniform nucleation. I think that is another insight. We have to improve our assumption for the model. But you are right. At the moment we assume nucleation start from the surface. Sorry, start from the substrate, and then definitely you can make assumption that nucleation can start from the surface of tungsten carbide. But that is another things I think we may discuss tomorrow in detail, because I still have some more slides. But that's something just for us to think about what is a real nucleation condition in additive manufacturing. If you build layer by layer, is that going to be the same as a nucleation when you do the hot rolling, or in the casting, in the forging? Probably we need to think carefully. And how can we identify the nucleation from the particle or whatsoever? I think this is interesting question, but I think what we a bit reluctant to do is actually we don't have enough experimental evidence to support what is a nucleation condition that we can use. Yeah.
One more question. So, how did you calibrate? In one of the slides, you have showed the temperature measurement using your thermal capture.
Yeah, understood, understood.
in that motion, and if this becomes more significant in case of laser powder bed fusion because the speed is little
Yeah,
fast because of the gamma phenomenon.
I think you are right. I mean, but previously what we did, we also having some thermocouple as well to measure, but definitely not directly to the the the, the melt pool, but to the substrate to calibrate that. It's indirectly. Again, something to improve in terms of experimental setup.
On axis, but for off
Understood, understood. Yeah, and that means in the background we also do some other verification from substrate, for example. Yeah. But I appreciate your point because I think probably I'm not sure we have that detail because this is about in situ monitoring now, your question. I'm not sure I have enough evidence to show you, but I assure to you that a lot of people looking at this using infrared camera or whatsoever. I don't know much, but they have someone trying to get more predictive thermal imaging now to validate the model. Again, some synchrotron people quite decline to use the emissivity to say about thermal field, but they said it's just indication of higher temperature. That's it. We cannot give absolute number. But your point are valid. This is need further research, actually. Yeah. And taking care of experiment. Once you appreciate that, you will set up accordingly, and that will improve our model validation as well. Thank you.
I have one more question. What basis the corrected tungsten calculation?
Say again?
What basis the corrected tungsten calculation?
As I said, high melting point. And then, okay, if you look at in nano composite area, there are so many. Okay, you can answer this in different way. Is one way is probably, but it's not good answer. Is that company probably suggest using that, but from the physics understanding, we may try to calculate the we call particle. What I'm trying to say is actually there is a work in the nanoparticle things that you can calculate the attractive and repulsive force of the particle, because finally you want this one to be dispersed in the pools of domain. The particle that introduced into the system will have an impact on the viscosity of the fluid, right? And this as a function of composition as well. Again, this is the subject of my future paper, which is actually if you do if you are in this field, nano composite, because it's a metric composite, right? Even it's not composite, it's just a reinforcement. Let me put it that way. You will see that for different systems, there are composition dependent that give you quite dispersive arrangement of this. And like titanium, you may need titanium boride. If it's nickel, you may use boron or something. For example. So based on the empirical study previously, I think that's probably better answer. We chose tungsten carbide. Higher temperature as well, we make sure that doesn't melt, and also it doesn't impact. I think this is important. Another version is that it doesn't impact very much on the property far from steel. Even it's expensive, tungsten, but we use quite little. Yeah. Anyway, that is a big topic. I think because now we focus on microstructure modeling, I think if possible, I try to identify and wrap up this part first. So. That is tomorrow. That is tomorrow. We have lab session tomorrow. Detail, we can ask 3 hours. This is just the beginning, actually. So I'm cover the physics of it. So we can actually, the challenge remain in this is actually, okay, as we know, manufacturability of some new advanced material. And what is the multi-scale characterization that you said, from very detailed new creation until grain growth or whatsoever, we want very detailed characterization, or we call high throughput or multi-scale, whatsoever we call it. And then still cracking is also remaining an issue. This will link to the next topic later today. I mean, second lecture today. And then the residual stress development is still an issue. This one, how can we link this fluid flow, melt pool, microstructure, and then the property. So having said that, just to when you understand the previous microstructure modeling, I want to use a last 8 minutes here to wrap up what happened yesterday. So yeah, I think now we may get more confident to use this kind of model to predict what happened in additive manufacturing with I mean varied assumption made into the domain to actually try to understand what is the resulting microstructure after you have a different scanning pattern. And this one also quite complicated. So this is something I've shown you yesterday as well. This is also part of microstructure. But rather than solid-liquid transition, this is solid-solid transition. In kernel 718, you will see that gamma prime, double prime, delta actually can be predicted across the 30 millimeter build here. And then you will see that the distribution of this particle is quite different from what we think. So spatial care is needed to actually take care of this. Otherwise, some part will be tailing off, probably at the base or whatsoever, because of residual stress development. So there's so many ways to do this. First, change the thermal field, right? Some way, somehow, we change the thermal field. But scanning this, going to that, and then come back to scan this. Leave some time, or some way, I don't know. But this suggests that if you do something constantly over the time, you will pile up the heat, and then intrinsic heat treatment will kick in at the bottom here. And then that's why the particle will concentrate it at the base material here. And this actually contributes to distortion and residual stress, as I said before. And if you want to choose to do post-treatment, like hipping or aging, you can actually change the morphology of the secondary phase. But how this actually work? Again, we can use the synchrotron experiment to calculate, approximate the volume fraction of the phases once under the heat treatment, which we do. We published in 2023. I think that is multi-scale characterization. I think I have something to present next lecture, yeah, on that. And what we want to do is to bridge over, I mean, this process science, that what we say, science push here, we want to find a framework that we can select any composition and then come together, not composition itself, but also processing things as well, to give the kind of manufacturability, or I would like to call it material passport. So this one will be capable to process this material using additive, and then we can come in a package. And then this is the thing yesterday we talked that this microstructure will change your property as well. This part is actually next lecture. And this is an example. You can find more information from the new nickel-based superalloy from this actor paper. I think not in place. This is already published, 4 years ago, quite old now. And then you can look at different alloy composition. You have different cracking. This is solidification cracking. There is some liquefaction cracking. And this one actually ductility dip, something like that. So each composition gives different mechanism that driven this crack, especially some location here, validated with the detailed characterization. And then you will see that this, if we come up with a new composition with better design, you may be able to get crack-free sample. And these can feed into the information, into the information back to the process design again, because we try to close the loop of the process science that we're talking about. Again, this is the same slide as yesterday, but just to recap that, how important, how they link together. Because just only this computational design of 10 million composition is probably not enough. We need to feed this composition and see whether it's processable at which condition, optimize it. In class 7 and 8, I'm sure everyone said printable, but it means, I have a slide next lecture. It doesn't mean that they can print every condition, right? It means the window of printing condition is wider than others, but you will get some crack as well later. Yeah. And then high throughput methodology, just remind you now, I'm trying to close the dot, to fill the gap here, hierarchical microstructure. I hope I can do a job better, I think. From now we have powder, we have heat source, we have microstructure. And next is about linking this understanding to property and quantitative metrography. So what I said in the additive manufacturing community is that we know the process is stochastic, it's not deterministic. We know that we need to find the distribution of the noise of the signal that we get. It's not just about one single number, it's a distribution. And then we try to reduce the distribution as much as possible to get better control of the process. And having said that, I don't want to spend time reading this one, but just to summarize that the transition of liquid solid metal during the melt pool simulation is important to tell you more about microstructure development. And definitely microstructure development will be important for property prediction later. And this is something we cannot compromise. We need to understand this. And this knowledge can be extended to do many things, like couple temperature field with thermal fluid flow. We can use to predict precipitation, grain growth, and also crystal plasticity later for the thermomechanical simulation. This is not my field, crystal plasticity, but I used to work previously, which I will show some example next lecture. Grain growth, density growth, this is something of my interest. I'm a physical metallurgist. I'm looking at the phase transition because that is the origin of everything, right? If you know the origin correct, you may get better assumption for your thermomechanical simulation. And then the powder is still a problem. What I say the problem is not really the problem in the sense that problem for us to simulate, but problem for the society to understand and resolve, because the powder production is an energy intensive process and it can sometimes waste a lot of powder because you cannot recycle it. You may need to have a way to looking at this detail carefully. Like, the dependency of the shape morphology, dependency of the oxygen content in the powder, what is the contribution to the melt pool dynamics? Again, there is some modeling already published, I think early this year, end of last year, regarding that. So there is some future topic that we can looking at. And definitely without this understanding, we cannot go to the AI machine learning based model. So I want to end this slide of lecture with knowledge without technology is missing, but technology without knowledge is impossible actually. With the high things that you want to do in the flying car, kind of, electric airplane, and also this, what is that, ultrasonic aerospace. So thank you very much. Yes. Oh, that's subject to the further research, I think. We need a big project to do that. At the moment, we are probably only the very first field group. Yes, but in terms of the upscaling, it's actually, I think it still needs a lot of calculation, and we can talk about that in the machine learning session, actually. How can we scale it up? I think there is some important thing that you want to.
Anyway, you can discuss later.
And we will talk about that as well in the next lecture. It's just beginning, actually. Yeah.
seen this attendance form, but somebody is not signing. So this is very important. Ensure that you have signed on this forms who are not signed daily. Yeah, please do that one. And one more thing, we are going to circulate one form after the break. You check any spell checking. This is for certificate preparation, right? So we put the last column as a name in the certificate in a capital letter. So if they are finding some deviation, then only they need to write, or everybody write. Yeah, if you find some deviation in your name against your name, just you put at the remark at the last column with the capital letters you mention. So if everything is fine, you leave it. But if there is any deviation, kindly mention at the last column, the capital letters, right? And one more announcement is tomorrow we are going to have some sightseeing, maybe the local visit. Maybe we can by 4:30. Yeah, and then I will ask the bus to park here by 4:30. So don't take much time. So we'll by 4:30 we have to start. Why? Because we are planning to cover 3 places within the city only. So one is a fort, another one is temple, 2 temples. One is Bhadrakali temple, another one is a 1000 pillar, that is a historical. Yeah, and then yeah, these 3 places. If you cooperate, if you start by 4:30, we can finish maybe early, right? Yeah. Okay. Okay. Thank you. Then I will be passing this after the break. You check your names, right? Fine. Thank you.
It's coming. I already plugged it in. Not yet. It's coming. Yes, coming. Yes. Yeah. So this lecture will be continuing from the previous one, but give you or present you a different example of the thermomechanical modeling of additive manufacturing. I would say it's more like a fusion-based melting process. So in this case, as you may know, some of the experiment has been done in the single bead kind of experiment. So we try to mimic that to our simulation. So you can think as a welding cases or whatsoever, because people may do single bead with powder or without powder. But the point here is not about that boundary condition only, but it's about how we actually translate the information from experiment and then validate the model to predict correctly the additional space development. So this is based on one of my active paper in the fusion welding simulation. So this is the, in this slide, you will see the, I would say power of lasers actually lower and higher, and then this will change completely from the conduction mode to the keyhole mode, for example, and that actually changed the microstructure as well from equax to columnar grains. And as you may see here from a kind of snapshot, this picture may summarize already what happened here, and then what the consequence of this microstructure to property. This is what we are going to talk. And finally, we want to know this area, as I said before, this may lead to failure, like you see crack here initiate in this zone. So the presentation of this lecture actually comprise of some introduction and motivation. What is the aim and methodology that we're going to use for this lecture? And then again, you will see a lot of word of ICME or integrated computational material engineering framework that we apply for this fusion-based manufacturing process or fusion additive manufacturing. In this case, they are powder-based fusion anyway. And then in the term of term of computational fluid dynamics calculation, we want to capture 5 things here. The first one, the keyhole formation validated with high-speed imaging. Keyhole instability, steady state well pool geometry. All of this has been validated with some form of experiment. Fluid dynamics in the well pool, porosity formation with available experimental information, well pool geometry, and also temperature history. So this is what we call processing induced defect, because induced by the process. And then this next one is a microstructure. As I said before, we cannot talk separately from process, microstructure, and property. Things has to come in one go, in one package. So in microstructure, we're talking about well solidification microstructure, the linkage of the CFD to cellular automata and finite element calculation. Either actually it's a partial penetration or conduction mode or full penetration or keyhole mode that you use in industry. And then how can we actually talking this, apply this framework? Again, now it is important for the not mechanical engineer. You also need to understand about what is the material system you are looking at. This may change from system to system. If you talk about steel, you have duplex steel, or you have just like ferritic steel. It's so different framework as well from mechanical perspective, right? It's the same. So the model alloy we used here is a two-phase titanium alloy, which is gamma beta system. And then the linkage between cellular automata, microstructure, and the crystal plasticity. And how can we talk about the static property yield stress here? Again, the simplest, but it's complicated enough, believe me, to link this location-specific prediction. as you've seen in the previous lecture, that at different locations you may get different structure and hence different property anticipated. So just to remind you, this is the same as yesterday. So we are talking about fusion-based process. This may be applied to welding, additive manufacturing, and also if you don't want to, or you want to approximate the electron beam melting as well, this may be able to apply, or electron beam additive manufacturing. So the introduction of this is actually fusion welding or fusion melting, I would say, is a joining process, is a joining of material process, and across the various industry applications, including aerospace. I think I don't need to actually emphasize about how important of the fusion-based manufacturing process to you. But to obtain the weld integrity, or I would say the structural integrity, which means defect-free weld, we need to determine the location-specific property. And the approach we are going to use is integrated computational engineering approach. I kind of actually give you the result before actually I'm talking to you, but this is what we seen from experiment when we vary the power, laser power, for example, in this case, and then it changed the mode from conduction to keyhole mode. And this mechanical property as a function of microstructure is required for component design and process improvement. I think that's what I'm also emphasizing a lot in the past. And in this work, in this presentation, in this beginning of this section, we will talk about titanium 6-4. So it's required that you may see this is the experiment, again, inspiration from experiment. If you use the different scanning speed, for example, and then you control the laser power, you can actually change your welded microstructure or fusion melted microstructure here from columnar grains to E-cracks easily. If you use very slow melting or slow scan speed, this actually will come E-cracks. But if it's fast scan speed, it's just about 4 times faster, you will get E-crack structure. And this E-crack structure may be quite detrimental to the part or to the component that you are going to build. Like this, you will see this is the sensitive area. And then probably some of the simulation I'm going to show you now can tell you a little bit more why. So this is the design for process. As I said, we need to understand what is the strain rate and the scale that we are looking at. So we are talking about quite low strain rate in this case, and also quite micro scale here. So this is the simulation that you've seen yesterday, that I'm talking that we can simulate anything on Earth actually under assumption made. You will see here from the superplastic forming, spin forming, ring rotary friction welding, linear friction welding, and then machining here. I mean, it's all intensive and a lot of calculation and also solid mechanics needed. I think from mechanical engineering people, I think you know how complicated it is. And how can we actually now, all these are solid state forming, or this one is thermomechanical process. This is also thermomechanical process. But there's nothing related to melting. What we are going to do next is to motivate from that inspiration here to do some melting process. So what does an engineer wish to be able to predict on a well? I mean, on a well or AM, I mean, that's something we apply to AM later. So in order to do the thermal liquid flow here, we use fluid dynamics or computational fluid dynamics to understand the well crown trough formation, which is crown mean crown here, toes mean this one, right? Formation mechanism. Understand the keyhole phase formation. What is the vapor phase in the molten pool here at a high energy density well or AM. Predict the bead and the melt pool shape, and this is what we get from melt pool. More than that, we will get the thermal history, we get the surface roughness, we get the porosity as well. Again, this is something I haven't mentioned here yet. But in terms of the stress distortion, we want to predict the true process field. And then this used for solid mechanics. So as mechanical engineer, it may relevant to you more now. Understand the tooling or cramping constraint as well, if it's applied to your system. And this well in structure on integrity, that's actually related to the detail that you used before on the prediction of porosity and defect. And well-zoned microstructure in terms of grain size. Again, we cannot decouple all this from the mechanical simulation. We have to take everything together, right? Grain size, grain orientation, well-zoned microstructure, and then crystal plasticity modeling. In the welded zone material property. Again, this is the simulation from this condition unwell investigated. You can see some particle. This is not particle. This is a porosity which is induced during the process that's trapped inside the well. And this is a 1 millimeter thickness, I think. And this is what happened. This CFD framework we use to simulate the shape and the physical phenomenon of the well pool, and this has been developed. And this, to actually, we need to combine this in the multiscale modeling activity to predict the component behavior. So based on the thermophysical property and physical description of titanium 6 for material property, we can actually gain insight into the material behavior, especially the property. Like this. This is the melt pool dynamics. This is a melt pool envelope here with the crown and the toe, and try to predict the microstructure, what happened. Extract some microstructure, represent this well meant, and then you predict some property. That is the talk for the first part of this lecture. And then multiscale, this is a multiscale problem, as you see. And then CFD can successfully predict the keyhole. Validate with the thermal camera. I will show you a bit later, which you've seen something yesterday already as well. And then we link this Serratomata to the grain growth prediction, and link this CA to crystal plasticity model to predict the material property distribution across the well pool. And this component level property prediction is based on the homogenization. I think this is a term that you may be familiar more than me. It's homogenization and of full field solution in the multiscale modeling framework here. So in order to develop this modeling approach, I want to be a bit more specific now, not too generic like in the previous 3 lectures. So for this particular probably single beat problem, we need to analyze the micrograph of the cross section, because we want to actually calibrate our model as well. So the melt pool model has to be calibrated against the experimentation. So we will use multiscale multiphysics approach to use CFD to predict the melt pool, and then link this to Serratomata for the grain growth, and then link this again to crystal plasticity for the material property prediction. All linked potentially to get a stable finite element model for the component analysis. That is the aim and objective. And then in order to do this CFD, we need to include the real physical phenomenon. I didn't actually mention explicitly in the previous talk, but it's actually now. It's probably good time that we have the multi-phase material with solid, liquid, vapor phases. That means it's going to be, but in this case, in the simulation I'm showing you now, about to show you now, is just 2-phase problem. But 2-phase mean the metal phase and then gaseous phase. We will talk you later. And conservation of momentum and energy. We have absorptivity term. We're looking at the effect of surface tension, Marangoni force, Draghi term to damp the velocity at the solid. So liquid-solid interface term, vapor pressure, reaction force, and then we have evaporation. It's all this physical phenomenon has been taken into account, and we believe this is sufficient to actually capture what happened during the process. And this is what a schematic diagram showing a closed length scale, that this is what we do and what we want to achieve using different computational tools. Again, that's what I want to emphasize. Things have to be integrated. It's not just individual things can happen. And this actually from the melt pool physics-based simulation using open form you can use, this is in microscale, a keyhole formation, melt dynamics, porosity formation, whirlpool geometry, and temperature history here. So this is a kind of flow pattern. You will see what happened in this flow, and then the flow pattern in maximum velocity is quite reasonable, about 3 meters a second. And then this is the predicted temperature field. This is a heat affected zone, something like that. And then you'll see it's quite good agreement with experimental work validated here. And this, after that, we have the reconstruction of the melt pool. The linkage is so important. We link the liquid, this temperature contour of at the surface, liquid at surface here, and volume of this melt pool. We extract the temperature field of this one, map this one, mapping the cooling rate at the boundary here, at the boundary, because everything inside is basically liquid. So we want to simulate solidification for this problem. So in the next simulation phase, we use Xera Automata finite element calculation. I mean, this is an early stage. You may know the commercial software packages called Procast. It's by ESI Group. Quite expensive as well, but this is one of the EU Rolls-Royce project that I'm working long time ago. So just show you an example. So we want to simulate well microstructures, approximately the solidification, but not detailed like I show you previous slide, a previous lecture. And then the grain nucleation, growth and morphology and texture here. And after that, we link this microstructure reconstruction again using the, at the moment, that time, I think it's about 2014-15, we use Dream 3D, which is more robust Dream 3D now for the 3D microstructure reconstruction. Again, if you do a lot of EBSD serial measurement, you may use Dream 3D to reconstruct your microstructure for finite element calculation as well. So we use Dream 3D and PPM to write the Abacus input file because we need to link the software as well. So we need to do some coding, programming to define the boundary. It's not one single button to place this and everything come out on one go. No. At that early stage of development, we need to do this. And then we apply the mechanical boundary condition, which is actually derived from the melt pool calculation onto the boundary here. And then next step, we use Abacus STD, I mean, in the user-defined subroutine to actually simulate the two-phase titanium constitutive law using some dislocation density-based crystal plasticity code to predict the location-specific property, such as the static property yield stress here. And this is one of the example of the result. The solid dot represent the experimental result from the alpha beta phase here, and then you see the model in the open circle here is experimental, and solid line is modeling. This is a macro scale, and then that's what we are going to talk and focus more on this part for this lecture. So again, the key of this is the integration. I think you may appreciate that what I showed you previously is increasing the length scale. So you basically scale up to larger length scale from meso or micro to macro scale. So the baseline of this computational fluid dynamics with other length scale will need to consider what is a true physical phenomenon that require for integration. That is important. I mean, still this is a challenge in the computational material engineering community to link information from each length scale. And this probably very first of its kind that show, I mean, because the work has been published in 2016-17, so it's probably very first paper that we show this. And then the link of the Xera Automata to the location-specific grain prediction is important. Link of this microstructure to this location crystal plasticity-based model, but this is for titanium 6-4. It will predict the material property. And link this FE to component behavior. Again, is another matter. So integration is remain one of the more challenging aspects of the computational material engineering community. First is about porosity and microstructure prediction. This is I would say, initial condition for what we're going to do. So basically, just recap, this is the mathematical framework we use. Simple than the first slide, first lecture, which we will talk more in day 4, day 5, I think that one. So we will include the physics that just repeats again the multiphase material, solid, liquid, vapor, right? Conservation of momentum, conservation energy, absorptivity, surface tension, Marangoni force, Draghi terms, solid, liquid interface here, vapor pressure, reaction force, and evaporation. So we didn't show some other phases which is present here, but we focus more on the well pool dynamics here, what happened. And then you will see it's collapsing, and then it's, you see there is some instant that everything actually collapsed and come back again. So this may be better represent here, so you will see what happened. You watch carefully. This one will be, you see this part is collapsing and then coming back, and this oscillating all the time, and which is quite interesting. And I can say that after we publish the work, a lot of work coming out, and then you may see more and more in additive manufacturing that they can predict the dynamics of this very well, probably a lot better than us, the first approximation here. But anyway, we capture all the surface deformation, materials recirculation, so this may cause to this street of the porosity, which is trapped inside the fusion speed zone, and then they will have defect formation here. So if we take a snapshot at a different time scale, and then we try to look at this problem as a function of radius of the laser beam. Again, what we can change is just the beam radius. We cannot change the shape at that time of the experimental facility that we have. We change the beam radius from 200, 300, and 400. And this is because this is for aerospace application. They want a very clean, well-joined region at that time. So they change, and this is the dynamics of the melt pool, if you see. So if you use smaller beam size, you will get a very narrow, shallow, melt pool. And then the map of this is actually on the keyhole surface, so we call liquid vapor surface here. And you see that the temperature doesn't actually, not actually homogeneous. There's some absorptivity effect present here. You see some zone is yellow and red. That means some, due to the term we impose here. And then when you increase the beam radius, the melt pool become larger and larger. So we try to compare. And then you see the keyhole are formed due to the laser heat source here, heat up at specific location until vaporization occur and create vapor pressure, pushing away the metallic gaseous interface down to the plate. So it's drilling down to the plate. It's actually happen as well in additive, but the difference of additive and this, actually you have powder particle, which actually increase the surface area in your domain, and then this may change your absorption a little bit. And leaving behind some narrow, hollow hole give rise to smooth joining path. Again, this is application of this is basically want to join something at the end. But this is something you've seen previously. We use high-speed imaging of, at that time, is about only 10,000 frames per second. I think I heard that there are the maximum I heard is probably 100K frame per second, but I may be wrong, but I think this is the case now. So that means a huge amount of data generated. And this is the work carried out in about, I think about 11 years ago. So things may change a lot, I believe, since then. And then capture the keyhole formation at the edge of the material. And then you will see that the modeling and the experiment show a good agreement with each other. And then what is the keyhole instability? If we investigate a little bit more about the keyhole here, you will see if I take a snapshot, there will be some incident that, every 10 millisecond, I mean, I would say 10 millisecond for additive is too long. We're talking by microsecond in additive. So just want to show you the kinetic of keyhole can physically captured. Even we can say something we call fully developed melt pool. I don't want to talk, I don't want to say the, this is actually what is called a fixed melt pool. Is not actually fixed because you will say steady state melt pool, and you see some undulation and oscillation of keyhole is key for defect formation, especially for porosity. And it's happened that this research suggests it's happened at the melting front, actually. And the incomplete collapse of keyhole is observed experimentally as well, using the X-ray thermography here. And this is the same condition that we use for titanium 6-4. And this is a modeling and experiment has been captured quite well. If you can capture the full, I mean the collapse, what is that, incomplete collapse keyhole at the bead of the plate or of the material here. How well can we predict the melting front boundary? This is another question, because I mean, for this specific application, the melting front boundary is just about, if I remember correctly, this is actually 100 micron, and you talk about 1 millimeter or more than one, I think it's 5 millimeter thickness. So the length scale are so different. So how can we capture this dynamic? This is another question to ask. Again, it's open for research. Compare with general feature with the melting front here in available tomography. We compare with the existing result in 2012 here, and then because that time we carry out the work around 2013-14, and this predicted melt front boundary is about 100 to 150, yeah. But it's actually good agreement with what we do in the experiment here. And extra information that I want to emphasize is the melt pool dynamics. Is actually the we call fully developed shape. It's not steady state. I'm not saying steady state because we believe it's not steady state. But doing the 2 kilowatt laser here, which is a lot more than weld additive manufacturing now. But I understand now we're talking about 1 kilowatt laser for AM, or a little bit more, 1.5. But this is for fusion welding actually, so it's quite high laser power, and you have different beam radius as well, as I said, and this is the detailed dynamic around the keyhole, what happened, and then sometime you may get some melt jet here coming out from the melt pool. And this we can try to understand and predict the porosity, and we hypothesize that the porosity might come from the according to the modeling suggests a causal mechanism of the keyhole partial collapse, which is actually something has been proposed long time without any supporting evidence. But we have demonstrated that using the simulation that, okay, if we capture carefully some moment, you will be able to trap or get some this kind. This is model, actually outline from the model. You can get the residual voice which is left behind after this fusion melting here. And then on the top surface, you will see the track like this with some hole behind. I think this is something quite inspiring because we seen the same as well on in the experiment. And we use some experiment to validate using the X-ray tomography actually to demonstrate the pore formation. The pore actually form in the quite perfect spherical form. But I mean, having said that, not every pore here is surface spherical because titanium, we cannot map across, I mean using XCT, micro CT, we cannot map every single pore here, as you know, limited by resources that time. But now you can see more if you use neutron tomography, you may be able to review all the porosity content inside, but resolution is another problem. If you get to see larger view, you may compromise resolution. But this one, we take care of only one single pore or just few pore, and then we compare this morphology with what we predict from modeling. And this is the model we use to predict. And what is the important of this one is actually we try to estimate the location size of the porosity, which can be predicted by the CFD. So its location probably not quite similar, but again, we can capture what happened, and this is really the modeling. And then you can see that we also have the X-ray radiography as well to understand what is happening along the fusion path here. So we can estimate approximately the location size of porosity using CFD, and the pore distribution for the given process condition is captured while we use the X-ray tomography, and the pore is likely to form at the toe of the well of the bead, because the likelihood of the vortex flow, as I will show you earlier. Then radiography here show the distribution along the fusion line. And next step, what we do is actually we do some parametric study to simulate this CFD framework. So parameter we use is a plate thickness, well speed, and laser power. Again, this may apply to additive easily. So we use the envelope of the process parameter here considered for the design space in the large pore porosity. So you will see this is I would say prediction plus experiment. You will see something we call processing map. So we map across laser power, well speed, and thickness. But if you are a metallurgy in the phase transition people, you may think this is a tertiary diagram. No, it's just a representation of the result that we have. So we can identify the red zone. Red zone means pore is big, and also we should avoid. We should go to the blue zone or black zone here, ideally. But you're not gonna get zero pore if it's not if it's possible. I don't know if it's possible, but anyway, you can avoid the condition at the very intermediate laser power, but also kind of well speed is very low. If your well speed is quite low with the immediate laser power, you may be able to subject to the porosity area. And this is the sweet spot that we identify from the small DOE design of experiment we have, and also modeling to get minimize the porosity here. So we get some sweet spot. And at this lesion, we have this one, so it's highlight as concerned. So we should avoid this. So this is something quite harm and energy intensive that we come to this point, but this point will be useful for the next step for the microstructure prediction. So as I said, this is a condition investigated. If you think about additive manufacturing, the 1,000 watt or 2,000 watt is probably possible now for the new AM machine, which you may be able to have. But people not prefer to go to the full penetration mode because of the reason I just explained. It may be some instability in keyhole and trap the porosity behind the bead or in the structure, which is not preferable. What we're trying to do is try to understand how can we go just before the full penetration, but we heat enough of the material beneath the surface in order to get, but in this case, we try to present the extreme boundary, lower bound and upper bound. For example, what the microstructure happening at the conduction and full penetration. And then you will see, we try to predict the fusion zone basically based on the experiment and the modeling here using the micrograph here. And then we want to extend these, export temperature history to predict microstructure and the thermodynamics boundary condition to represent the heat source, moving heat source especially. Not just heat source, it's moving. One of the things of heat source model, there was some more detail if you like to understand, we map only on the surface. So it doesn't, it's a volumetric heat, but we map only the heat on the moving surface. So you will see something look like absorptivity that people measure experimentally. So this is what we do. So I think this is much more detailed now, this presentation, not just showing the result. We use the Visual Basics in Excel that time to export or map the temperature field. Again, that time it's actually 30 gigabyte of data has been picked up. It's just a single bit of the melt pool, let's imagine. And then we use Python to actually generate input deck for the model that we use. And in that case, we co-develop with the commercial package here, Procast. I mean, I'm now moving away for commercial packages using open source code. And then using the VBA to scan data and then pre-process the automation. It's about 10,000. I think it's more than that at some condition. It's about 2,000 boundary condition at the melt pool surface here. And you use Procast to manually, at that time it's no automation, but we need to automate this one by Python scripting. But anyway, we pre-process this melt pool boundary here, and then we execute the model for the grain growth prediction. And this is, at that time, is an interface that we see. So this is what happened. You can predict what happened of the grain growth solidification, and then you see the moving liquid solid interface. And this is a grain which is grow. A good question from the previous audience. They're asking about nucleation condition. We assume a normal distribution at the melt pool boundary at this time. But because it's valid assumption, because the parent material actually has the quite uniform, it's a rolled microstructure, so it's quite uniform after homogenization. So average grain size is kind of known for high standard aerospace application. So it's kind of valid assumption to make. I believe it's a 30 micron grain size at the raw or parent material. So we integrate this challenge by transfer across the length scale. So I hope you appreciate how complexity of the model, and in order to make it automate, it requires a lot of work, not just a material scientist. I appreciate my colleague who do a lot of programming things that make this work happen. And then we propose a proof of concept approach that we can allow user to access and manipulate the data. Important information that I want to say is that this temperature field is transient temperature, it's not static. So this required to represent the moving liquid solid interface. That actually pose another challenge in the solid mechanics calculation later, which I will show you. So now we map the grain size. This all predicted. So this is the predicted grain size from the condition that I proposed to you. So this is a PV. So P power and V velocity. So we see you can again the same, you get this hot spot and you get sweet spot for this processing. So in terms of microstructure. So to generate the process map here, a number of grain also important, because whether or not you represent the real fusion zone that we are looking at. And then this around the targeted design space to achieve required microstructure. Because some microstructure is very equax, some microstructure is very columnar grain, and they actually pose different property, which I will show you now. So in terms of microstructure, additional to what I show you, just the grain size, but from the coding skill, we can try to actually extract some information like the shape of the grain, 3D grain. We can calculate the volume, and then we can calculate the shape factor, which means we can surely quantify, surely quantify what is the grain. It's not just looking at it in 2D, but we are now looking at it in 3D and see the morphology in 3D, and then we calculate the shape factor, which means if it's smaller, it will be going to closer to circular. If it's larger, it's elongated, something like that. That's what it means. Or another way around, I'm sorry. Circularity is 1, sorry. Yeah, that means it's actually intermediate here. Sorry, my bad. Yeah. And then the shape factor here, constant. Yeah, if you see here, equals or closer to circularity, 1. If shape factor closer to 1, if closer to 0, it's more elongated. But you will have the shape, which is in mathematics. You don't have only circular and elongated. You have somewhere in between as well. But most of the time, you get the grain somewhere in between. Again, this kind of information, I think, is quite difficult without any now. But there is a technique called correlative microscopy that you can serial section faster than before. And then you reconstruct 3D to see the morphology of the grains. But this is what we did from modeling long time back, I would say. And in addition to that, we also can predict texture as well. Textures, I think I may think you understand texture is orientation based. I mean, compare with the growth orientation of the material investigated. So in this case, we predict beta grain. Beta is the body center cubic crystal. So I'm sorry, it is too material now. Yeah, and body center cubic, the preferential growth, which is a minimum energy that material can grow in this direction, is 0.01. So that means if something misoriented from this 0.01 direction, this is mapped on this figure here. So this is predicted. So predicted texture also we introduced in the fusion process. I mean, quite early as well. So this is something we can get from microstructure prediction, and then you will see that from the conduction to full penetration or keyhole mode here, the well microstructure are different. And I will talk to you more. The different here will contribute to the different in the property. And equax grain microstructure can seen as a partial penetration as expected. So, but full penetration is more likely to be columnar grain structure. So again, this is what we try to compare. So temperature field now microstructure you see is more equax, and this is predicted as well. So we haven't had any EBSD data. Just want to let you know this is the beta grain structure. So, but what you see in the experiment after in postmortem, it will be alpha phase, which is because it's transformed from beta to alpha, and this is the last phase, which is similar to martensite in steel. And that means you need to do another programming to reconstruct back or work out from crystallography what happened if prior to this structure. You need to transform back to beta. But anyway, that is a detail. So what we do, we link the code. So I show you in practice what we are doing, not just talking about that. So grain orientation has map on this space. So we have to communicate with Abacus, which is one of the greatest mechanical software that we use here. And then you will see it's not trivial. We need to map all information and then try to find a proper match to represent the microstructure we have. So we try to vary the mesh density, vary the mesh size from TET to HEC as well, and see what happened and how can we apply the algorithm to smooth the boundary. Again, there's so many challenges in translating model to another model, and this is something we try so hard to make this happen. And this is a concept. So we do the same from like experiment, but we do computational experiment as well. So we're stacking the 2D section and generate a 3D mesh here, Dream 3D. And we now try to run Abacus based on this simulated structure. And then this is we use in-house source code here to simulate. This is basically this is the result. So you will see that we try to replicate what happened in the in the as printed condition or as fabricated condition in this case. Another thing is actually now it's more about mechanical engineer. That's you may need to impose some solid mechanics. But this solid mechanics is not purely solid mechanics. It's just, I mean, what you see here is just constitutive law that we trying to impose into the crystal plasticity framework that we have. You know, in one grain that we simulate, it should be contained is about 2 structure when we see it at room temperature. So this will be lattice phase here, which is alpha, in the beta grain envelope. So, but this one, if you zoom in the inside, you will see there's some dislocation and the active slip system that actually promote or making the plasticity in this material. So this is, again, this is a solid mechanics framework by Hector Basotto and his colleagues here. So we apply this rule. This is a shear rate. I think you're very familiar with that. Dislocation density and then the shear stress thing. Yeah. So what you see here is a continuum dislocation dynamics framework that we try to apply this in a grain system, in an active slip system, using these things. And yeah, I don't want to go much because it's not my area of expertise as well. So we try to work with another colleague in the continuum mechanics people, try to translate this information across to another length scale, which is crystal plasticity for titanium 6-4. And now this is actually come to the point that I want to show you, I mean, multi-scale things from beginning until the property prediction. And this is a good example that we can show you from the global, because before we do that, we need to run another model as well based on the CFD result we have. We need to run another global FE model. I mean, we have the local model from the what I showed you previously. We need to translate across somehow to the global model to predict the pre-mechanical behavior, what happened. Because in reality, your part is big, right? You need to predict something happen locally. What is a mechanical representation for that microstructure? Because we are talking, again, that is another challenge. How can we know the mechanical or initial condition for this your mechanical model? And if you like, this is the microstructure information that we created. We select some part here, apply some thermal boundary condition and also mechanical condition based on the global model here. And we try to predict the, we calibrate first for the beta phase at the 925 to 1000 centigrade using some experimental work that they have. Again, this experiment is actually forged material, but we that is only the experiment we have at that time to validate the model. And then we try to apply this. Once we get some confidence, we apply this to the crystal plasticity model to predict the mechanical behavior. So this is another linkage. So we link later from lower length scale using representative volume element in FE to component level. Definitely we use Python scripting, abacus cube here, and then grain structure. We also fragment a pre-match FE model to CA to inform grain element set, and then we transfer this RVE, representative volume element, to finite element calculation. And output to the macro scale, constitutive equation of the two-phase material has been used. So this is the 9 condition that we have, and then we have 9 microstructure information here as well. So a different process condition PV in this case. So what we do is actually plasticity formulation. We dictate by dislocation density, I mean an interaction, and the grain orientation is significant impact on the plastic response to the external traction. And then we use this set interrogate data from CA to feed into crystal plasticity code. I mean, just to summarize here, information here, apart from shape, apart from orientation and the grain size here, had been fed into the crystal plastic framework and try to predict the property accordingly. I mean, this breed again at different strain rate, actually. Yeah, you will see this is the prediction. And the property prediction has been predicted based on the detailed microstructure of the two-phase in titanium alloy Ti64. I mean, during this fusion melting process, we assume that beta titanium would be dominant. Yeah, because that is some we call as solidified structure. We don't consider after they're transformed to alpha. We just concern about assume this is assumption made. That means we propose that the deformation dominant from the as solidified structure. So beta grain is considered here. The yield stress derived from this microstructure shows some softening effect. That means this is in the, if you think about in the bead, in additive or whatsoever, this will be the sensitive zone because it's softer than other zone, right? And that larger density of grain can be modeled in the future. Again, the next question is how can we scale up? Again, this is the big question. And probably it's worth £10 million project, actually, this answer, because there's some project going on in US as well, for example, exascale simulation for additive manufacturing. Again, this is just a very first proof of concept modeling framework we have. So we reconstruct this cellular automata microstructure with Abacus RVE using the UMAT, which is use material defined subroutine, apply the external traction to generate plasticity in a simple cube component. So we have microstructure really, and then we apply the boundary condition to simulate based on the global model that I said earlier. With the representative boundary condition, we can actually get some different in the full penetration and also what's that? And the partial penetration or conduction and keyhole mode structure. You will have different behavior from A to B. For example, in this one is softening, this one, another one is hardening. And that is something that we need further research to do more and more cases. I said to some of your colleagues, there's some group in USA just focusing on this work, but not actually used from CFD. They use from EBSD data and then try to actually rapidly calculate this one more and more and more. Example, Professor Koch from Johns Hopkins, I think, if I understand correctly. He is famous in doing this. I'm not, but just want to show you this is the direction that we want to integrate the information. And then, yeah, from the implement of this framework at a sub-model level, because as I said, this is just a volume of one in the big model, right? So this is a representative volume that we use, and how can we respond it back into the bigger model is another question to ask, but not here to address, I'm afraid. So we believe based on the information we have, we may select proper constitutive behavior for the material that you use. That's why I said important of microstructure is variable. So we will looking at different stress component as well, strain, plastic strain at different component as a function of microstructure here, and feed into the global model. And again, this linkage is not really there yet, but this is just a proof of concept for a condition investigated here. And just want to summarize the first part, which is taking me quite long. So we can say that the framework here, I would say fusion process is applied for additive as well, as you know, fusion well process. But the CFD successfully showed the capability to predict the well-induced porosity, and this validated again the X-ray imaging technique. And this integrated to the cellular automata grain prediction model. We do a lot of data processing to generate the microstructure, to represent the real microstructure from simulation. And this has been integrated to the finite element calculation using representative volume element approach. And this one can predict the component in the submodel analysis. And we believe this development of the crystal plasticity as a mechanical engineer, I think I need to corroborate with you, is actually going on. And what people said, want to do the, integration of the model and also machine learning. We may need to have a successful linkage of one model first and then try to approximate based on this understanding to future final element RVE model. And the process map that I show you, this is something us as an engineer want to have it based on crack criteria, based on whatsoever. For me, probably based on porosity, because we believe it's going to be based on microstructure prediction. This is something that model can do, probably rapidly generated the data than experiment and less expensive. Thinking about Type 64 material, quite expensive material, you're not going to produce thousands of conditions to have the map. But hopefully we can have the model with, probably in the future we may use quantum computing to accelerate the calculation somehow. I don't know. Yeah, and then this multiscale approach here has been developed to model this fusion-based process under CMV framework, and then CFD provide understanding of interaction of heat source and the material, provoking the keyhole dynamic, porosity formation, and whirlpool geometry to has been rationalized, validated, and predicted. Dynamic temperature boundary and shape of this has been linked to model the solidification in the conduction and keyhole mode, if you like, and then it showed that equax grain actually form in the conduction mode and the corona grain mostly found in the keyhole mode. Again, this one is carefully observed in the condition we know very well. So this nucleation condition, I think, is varied to assume, but for additive, it's so dynamic, so kinetic. So we need further study to confirm what is the real condition that represent the process. I believe it varies from material to material, condition to condition as well. And the grain morphology reconstructed for crystal plasticity calculation using this new two-phase titanium alloy constitutive law. Again, if you change to nickel, things may change. If you change to steel, things change again. I think you appreciate that. And the steel, you may change a lot because steel is so powerful material on Earth that you have so many variety of microstructure which actually contribute to different behavior, a lot of behavior. So use stress prediction, which is static. We're not predicting fatigue yet, which is the things we want, because if it's rotating part, fatigue may be important property, but it takes a lot of time and effort to make that. We will cooperate with other groups around the world. So this is the first part that I believe this can translate to other things. For example, like rotary friction or linear friction that I mentioned earlier. Okay, I was thinking there is another part. Sorry, let me. So, yes, I think probably it's good time for discussion. I think it's actually I speak too fast, I would say. Do you have any question? This time, I think I don't take any question during the, yes, please. Say again?
Does the microstructure modeling consider constant underpinning, or it takes like variables like partition coefficient, local thickness from different values?
Good question. The answer is no. This is a simple solidification model. Yeah, because let's imagine we're talking about few thousand, and that time is actually 2013. It's just a proof of concept that we integrate everything. As people said integration, but no real example. And we try to create the first real example that we integrate everything And this is what the thing. So at that time, we co-developed with the commercial software packages to apply this. So we need to use simple kind of just follow the thermal gradient direction to grow the grain. Yeah. But complexity can be added, but if you have a lot of computational resource, I think that's fine. it's okay, but yeah, it's not just easy and simple. But we can do that now. But let's imagine we're talking about not only 9 microstructure here. We're talking about, actually we simulate more than this, but we just show you the 9 microstructure here. So thinking or considering that factor with the computational resources we have, if we are national lab, probably yes, we can generate tons of data without any concern. But we need to compromise with the resources we have as well. It is just a proof of concept. So the model we use is not what I present you last lecture. No, it's just simplified version. But we hope we can simplify something based on more complicated simulation that we have and take some important information to get this microstructure. That is the aim, because we cannot simulate everything in very physics-based simulation all the time. It's impossible in a component scale analysis anyway, right? But people talking about what is the important parameter, important information. That is the key for this kind of model to tell, I believe, yeah. Is that okay? But if you fancy, if you are a metallurgist, you may want to do very detailed segregation profile. It's okay, but it's not in this length scale simulation. It's another length scale of simulation. You may need to do surrogate model for that and then export, global, local again, find a numerical way to do that. Yeah. Oh, that is assumption made. This structure assume is a plier beta grain. So we assume that the deformation taking place during beta transformation. So because after about 950 or 850 to 950, based on the different grade of pi 6-4, the beta will transform to alpha, right? And then we assume that deformation taking place just before that. Assumption made. Yeah. in this case. But again, the detail. I think I will show you example. I think probably it's not, if not tomorrow, the day after tomorrow, that we use direct energy deposition, apply detailed microstructure. Apart from solid liquid gas transition, transformation, we apply solid transformation as well. You will see that it will change the microstructure from beta to alpha. And that is the detail I'm going to show you next lecture. But for these cases, no. Assume that things happen before that. But I appreciate you yourself. But constitutive equation may be able to capture what you said. But the complexity had to come to constitutive law. That means you need to say that this is a pi beta grain. During deformation with the cooling, you need to impose some crystallographic orientation that involves some transformation, and then you introduce some deformation due to that transformation. So complicated. Yeah. Again, this one is, I would say, is a representative result that we show you. It's probably a bit overestimate, because beta and alpha, some of them actually, because we assume that we simulate the beta phase. Is that okay? And then with beta, if you change BCC, is BCC beta. And then if you change from equax to columnar, based on the constitutive law we have, it behaves like this. Again, This is just a simplest plasticity model we apply. Detailed calculation needed. We just, this is a proof of concept framework that we proposed. Yeah. So I appreciate that, but I think that suggests that detailed research needed for us to work on. And then we need some mechanical engineer to help us. I'm not mechanical person, I'm material people. Yeah. Yeah. We plan to do, but not yet. But I would. This is good question. The answer is not yet, because if you impose that porosity, you may need to impose another complexity on the fracture mechanics, which is not yet done. I'm not. I need to collaborate with some other people, maybe you. But not yet. We haven't done yet. But in principle, yet we can generate that. We can select the zone with porosity, which we have, but I haven't shown you here yet, because I think we have faced some numerical challenge around that feature. Yeah.
Suppose we have to predict the system of predicted path. So there are different ICM frameworks. Suppose in one ICM framework we go from thermal fluid prediction, then we go for solid transformation, and then we go for directly residual stress prediction. And in other framework, if we go from thermal fluid prediction to this solid transformation, including crystal plasticity, then we go for residual stress prediction. So which is better? Which either of the two?
Depends. I think it's heavily depend on the material system you investigated, depend on the condition you investigate. I think, again, I think I don't know the answer, which one is better. But for my condition, let's say in titanium alloy, I think this is probably the best way we need to take, but it's still challenged as numerically and also, resources needed. Numerical challenge is one thing, require a lot of resources. But you said, you asking the right question actually. But in order to answer your question, we may need to try both ways and see whether we get the same result, or the result that we obtain from both ways is actually the same from experiment we observe. Again, modeling is just need to work with experimentalists to make sure that this is the model have predictive capability. I think it's a subject of future research.
One more thing, when we doing this speaking modeling, then we consider RBs. So in one of your slides, you have shown that you have considered the global boundary conditions on the RBs. But in most of the cases, we use the automatic boundary conditions while using RBs. So what basically this global boundary conditions are referring to?
Yeah, global boundary condition will impose you the initial mechanical field, because we don't know what is the initial mechanical field for this situation. In this situation, it's just, let's say if you want to repair using fusion welding, for example, you need to cramp the both end of the part that you're going to build, right? And then you pass the laser through. And we want to know the initial mechanical field that happened to this structure, what happened, and then we want to see how this mechanical field evolved with the structure given here. So that's why we need, that is another complexity that I think in the solid mechanics people know, that what is a representative, physically representative of the boundary condition that gives a meaningful result to you. Yeah, that's the reason why we need to do that global model. I think you have who other, yes please. Yeah.
My question is regarding the previous lecture on the microstructure model.
Okay.
You model was developed on cellular method, but there are other models like LVM, that is original method. So I want to just based upon your experience, which method is more suitable for accurate prediction of microstructure, because I am just a beginner in this microstructure.
Yeah.
I have gone through literature that I found researchers are using both the models to develop a safe modeling to test microstructure.
Yeah.
So which is
Mm.
more suitable and more accurate for microstructure?
Yes. This is very good question actually. And microstructure modeling in additive manufacturing is become more and more popular. Previously, I would say for the simplicity, I think the statistical approach like Monte Carlo or the lattice Boltzmann kind of things, it's just simple, it's too simple, I would say. There's no physical meaning there. If not, you have to create a new framework based on that numerical framework to impose some physics. But I find it actually, I want to highlight your question. You say accurate prediction. Again, what does it mean by accurate prediction? That means you need to correlate with experiment. But if so, we can impose more term, let's say in phase field or seratomata, that addition to the equation easier, and then we can. That is my preference. It may be wrong from some other people. They may say lattice Boltzmann is better, but for me, my preference is phase field or seratomata, because, for example, if this microstructure in additive, especially now, you have the other process you may know, it's called field assisted additive manufacturing. So if you want to impose that as a function of magnetic field, electric field, or whatsoever, you can do it with physical term, physics-based, tools. But for that statistical approach, I'm afraid it's so, yeah, it's not something I prefer, yeah. So I believe this may be more accurate than other approach, yeah. When you can incorporate all physics-based equation or principle into your microstructure is more preferable, yeah.
And one more question.
Yes.
When you are discussing about the multiscale modeling,
Yes.
as we all know that to have a very tiny melt pool, we need to have something like laser spot diameter of 80 micron or something.
Mm-hmm.
But you show something like atomistic modeling where you have shown a picture of molecular dynamics. That's
Yeah.
a representative. So how feasible is that even though the melt pool size is around 100 or 200 microns,
Mm-hmm.
but how that larger scale can be converted into atomistic modeling to simulate the process actually? That's just a doubt. Like
Again,
that small
we need to be careful about this. So we need to ask the right question. So what is the use of the atomistic simulation? I would say to you a few examples. Like atomistic simulation is not going to simulate in a melt pool size. Do you agree with me?
yeah, that is right.
Yeah, and what we need from atomistic simulation is actually some property that we cannot measure. For example, the vapor property. For example, some interfacial energy of something. I don't know. That kind of property we want to link from lower length scale to meso length scale. So that is the use of the first principle or atomistic calculation, actually.
Actually, my question was only that whether we can simulate that process modeling on atomistic, or we
No.
use that.
If you have quantum computer, probably yes. So you may know that there is some paper from China, I think probably Tsinghua University, on the wetting process. They use one bead of the droplet using atomistic calculation. Yes, it's possible. But I think your domain will be limited by the computational resources. But again, I don't know what is the use for that if you don't have the target property, or because basically it is a electronic property that you get from atomistic calculation, right? That people want to do, or the some thermophysical property. If it's the case, probably yes. But if you just want to simulate melt pool, I don't think it's also. It's not the right tools for that, I think. Yeah.
So my question is regarding cladding.
Yes.
You have mentioned that in last class, like as printed model you are selected, or are you done any surface treatment? Because what is the role of surface roughness over there in the cladding?
Very good question. we have simulated something on the surface roughness. There is some impact on that, but I think it's probably better. I think the detail of that will be discussed tomorrow in the lab session. So we dedicate 3 hours for that. And another reason, because I'm not actually, conduct this work myself, is my postdoc. So it's better to ask him, and I can help tomorrow. Yeah. Yes. Are there any other questions? Yes, please. Yes.
For all the CFD simulations for single tracks,
Yes.
multi-layer, what are the thermophysical properties? Means you use all the properties at room temperature, or do you go for high temperature?
No. We use a temperature-dependent property available in various forms. This is a good question. This is something I suggest to my research council in UK as well. So the data that we use to represent this case is actually based on the data that we use for casting forging, which is not optimized for additive manufacturing. As you may know, the powder and the bulk property are different, right, from mechanical model or mechanical engineer perspective. So we need some way somehow to treat this property based on whether you use the term like 1 minus porosity of fraction to lower the stiffness, for example. But you may need some way to treat this property. But we don't have a kind of good data set for powder property at all. I know some company has done that, and they may sell you quite highly costly. Yeah, I think I know some company, for example, a thermodynamic company like Thermocock, that they developed the non-equilibrium, the database for AM, and that means the database there is so valuable. Again, you are asking the right question. Still, I'm not saying problem, but I would say the area for improvement. And this can be calculated or done by probably atomistic calculation. I'm not sure, because atomistic calculation, they're not very stable at high temperature as well, only 0 Kelvin, right? For the sake of finite first principle calculation, there also has some assumption. So how can we represent that? But they still have some elevated temperature first principle calculation, which is more effort and resources required for doing that. Again, you're asking 10 million project question again. Say again, I not get.
So suppose if you were referring to the non-equilibrium temperature dependent properties of the material, okay, like TI64, ALSI.
It's not non-equilibrium. We said temperature dependent property.
Okay, so due to the non-equilibrium nature of the components, means precipitation and all those things, there could be some effect to the temperature dependent property as well. So those effects will be more prominent below solidus temperature.
You ask very good question, but the thing is, that's this assumption. We say that this intrinsic property we use, thermophysical property, doesn't change. That is the assumption made during the rapid heating cooling, because we believe that's an intrinsic property. Again, you may see otherwise if you have very detailed characterization and prove that it's not. Again, we're still waiting for experiment to inform us what is the things. Yeah, that's very good. But I mean, if you see a rapid certification community, they use probably for different material system, they're probably looking at metallic glass, something like that, right? So it's again different application for, it's not structural material, I believe. But I mean, we may need to, I mean, that's good. We can generate some idea for research on that with some people in the field. But for me, I don't know yet if experiments suggest that, I think we need to find a way to simulate that. That's what I can say. But at the moment, the assumption we believe, we assume is that the property is intrinsic to the material. Whether or not it's imposed, whether or not the effect of the non-equilibrium rapid heating will affect that, we don't know yet, actually. Yeah.
Thank you, sir.
Any other question? I think rather than question, you may feedback what we have how to say lecture for in the last. I mean, this is the fourth one now. Probably it's halfway through my lectures part. I mean, definitely. I mean, 2 sessions tomorrow. I will deliver first session, and the second 2 sessions after that will be together with my postdoc, which join online. I mean, so far, what do you think about the lecture? Is that good, useful, or something you want to add me to add more, or you think I should leave more time for question? What is the thing? Because otherwise, I will occupy all the time for the lecture. Yeah. Are there any suggestion, comment? Sure. Okay, I will rearrange accordingly then. So something like this is better, right? Rather than talk. And actually, I also don't know who here are PhD scholar or PhD student here. Wow. Okay. So your research here is based in IT, Warsaw, or somewhere else as well? Say again? Other institution, okay, sure. Say again?
Like validation. We
Yeah.
ask about validation because of always percentage of error, how much we always approximation what we are getting. So how do we validate whatever the result now stress strain curve, whether it's isotropic or anisotropic, orthotropic, which type of properties you consider to get that simulations?
Yes, you are also asking the right point question. So actually, we base on the data currently available for us. So you are right, the one we use to calibrate the model is a forged material. So it's not actually the right processing route that we use. But again, this is I'm not saying problem, but this is an opportunity for research to do more like industry to generate data. Because as you know, forging or casting is a long-standing metallurgical process. So they have a lot of data generated. So we cannot ever generate those probably worth several million pounds of data, right? So we need to borrow that. You asked the right question, actually. So the suggestion or advice to the company is that I think now they are doing that, to generate their own data based on the material they have. Because even you're talking about the grade of steel, but you still have different grade for different company, for example. And that will be valuable data for you. But how to use it, that is the question. Because when you have the data, you may use for machine learning, you may use for CFD, you may use for blah, blah, blah. But I think to use that is the question. Whether or not this will change significantly from the database we have, or you may find something completely different saying that this process alter the thermophysical property. Again, I don't know, this is fundamental question which I cannot have the answer now. I also don't know the answer as well. So we don't know, but this is an opportunity for research, actually. Or probably first principle calculation can tell us. I don't know.
For isotropic, but when it comes to
Yeah, anisotropic, yeah. Yeah, I mean, something in the micro mesoscale level, we all know that what happened, but you're asking about intrinsic property, right, of the different material with different processing. I think you may appreciate with me that if you do casting, I think you may see some paper talking about this is a casted material, this is a forged, this is a welded, this is a wrought material, hot working. They're all different property. And that's why I said this is an opportunity, I would say. I don't say this is a problem. This is an opportunity for us to collect it or make it even better again, it's require a lot of experiment. Again, what I said here, you need to inform me, oh, Shinapat, this is not right. We need to calibrate with this set of data instead. And then that is the way to go forward for modeling to predict out of range property that you may not have, or yeah, because we need to identify that as well. I would say this is a kind of working framework, just show proof of concept what we have. Yeah. Is that okay? I think that is the key, right? Otherwise, there is no single project funded at all, because if I do everything already, I think there's a lot of things to be done. Yeah. Okay, I think it's time, Professor Kumar. What should we do? Or?
Yeah. Thank you for your nice lecture.
Thank you very much. Yeah.
Yeah, and then now, yeah. Yeah, now we'll break for the lunch and we'll come back at 2 o'clock. Yeah.
It will be lab, right?
Yeah, it's yeah.
Labs, not me. I think it's your.
So it is 2 o'clock here at the same place.
I'm talking too fast. Second.
The timetable.
Second.
Afternoon session, second day. And this session is mostly about on the topology optimization. So, and with the continuation with the yesterday's talk, my talk on design for AM, it is connected to the, which we have understood from the DFAM presentation. So, one of the biggest advantages of additive manufacturing is we can print the bionic designs, right? That is normally light-weighted structures. So weight reduction, which we need to in automobile industry, medical, right? And even automobile with specific to weight reduction, or Formula 1 cars, right? So that is another area where, and even bikes also, if you see the race bikes, right? So wherever you have a light weighting or the weight reduction, and topology optimization is going to give, say, the best design, and then further you are going to fabricate through additive manufacturing, right? So in this session, briefly we'll give some aspects of weight reduction, and especially say with the medical application as well as the aerospace applications especially, right? So we'll demonstrate a software like Topology, so how we can reduce the weight, right? So, and also lattice structures. We are going to cover two parts. One is topology optimization, and other one is a lattice designing. So that is through Topology software. And we are going to show you the one medical application, the bone, and other one is a lightweighting of aerospace and the automobile applications. So may I request Srikanth to take over.
Am I audible? Okay. Yeah, thank you, sir. Good afternoon to everyone. Myself Srikanth. Today I am going to present a weight reduction methods. This will be very fun, and I will see this. So weight reduction, there are few methods are there. I think one method you know that we will see first. Three methods we are using. One method is the material substitution. Means what we are doing means traditional designs is there. Like suppose somehow how can we reduce the weight means using the lightweight materials, that is aluminum, titanium, these things we are using. Instead of steel, we are going with the aluminum, titanium, so that we can reduce the weight because density is lesser for the aluminum, titanium compared to steel, right? So that is the one method, by substituting the material in place of steel. We are substituting the material. The second method is the structural optimization. Like in the structural optimization also, shape optimization, size and topology optimization is there. And mainly we are using the topology optimization. The third method is the lattice structures. Lattice structures means this is not a not a with new term, very like we might have often the term in the schooling days also. Lattice structure is the BCC, something like that. Crystal structures. That only there only we get inspired. And the classification of the lattice structure is strut, TPMS, planar, that we will see in the coming slides. So this is like I told you, right? This is the past. I mean, in olden days we are right now still we are using material substitution, and presently we are using the structural optimization. And in future we will use the right now there is a research is going on, but industrial oriented point of view, like very few are using. So in future they will use this one once we get the standardization, these things. So these are some of the lightweight materials and the applications and the suitable EAM process. As you can see, in lightweight materials, metals, polymers, composites and ceramics is there. And where we are using, I told you, right, instead of steel we are using titanium and aluminum, and that we can use it in the aluminum alloys, we can use it in aerospace and automotive application, and titanium we are using for the medical implants and all those things. And these are some of the EAM process that we can use it. Yeah, and this is the one, like in automobile, what is the material we are using, and this is the structure. You can see like so much of material is carbon laminate, means composite we are using on the outer body and all those things. And there is a confusion between the design engineers. Actually there are two terminologies are there. One is like generative design and the other is the topology optimization. Both are like a apple and oranges, not like apple and apples, okay? Like two sides of coins is there. On one side generative design is there, and the other side topology optimization is there. What is the difference between, first we will come to know what is the meaning of generative design. You might have heard this term design and generative separately. Like if I say like I think everyone heard about the ChatGPT, right? So there if you heard means you might have heard the generative AI. Same thing we are using. Means we are giving the some prompt is we are giving, and it will generate the text, right? It will generate that answer. Same thing here also we are using the same thing. In Fusion 360 this we will use actually. There is only one software is there which are working on the generative design, that is Fusion 360. But topology optimization, so many softwares are working. So in that generative design what we are doing means we are entering the some prompt and everything. Prompt means I am saying about the ChatGPT terminology, because right now we didn't have the software. So but topology optimization we will see. And so we are working on we are entering the prompt means we are giving the some constraints, objective, everything we are giving, so that according to that design it will generate the 3D model. That we call it as the AI models, actually artificial intelligence models. And the topology optimization means same thing. It will work on the AI model, and this will work on the some mathematical algorithm is there. There is one person is there, like his name is Bendos, who is working in the professor of the DTU, I think Denmark Technical University. There he is a professor. He is the one who found this topology optimization method. Like he is using the SIMP algorithm, solid isotropic material with panelization. He is a mathematician actually. So there you can use that algorithm. Based on that algorithm, that will remove the material actually. So we will see some of the examples with which is topology optimization, which is generative design, that we can see it, okay? And some of the inspiration, like anything we are getting the inspiration from the nature only, right? Same thing, we are designing like previously tree means like complete solid is there, right? Some material we are in trees, but still the thing is it is serving the purpose, right? The main thing of the motto of the generative design means it should serve our purpose, whatever and it should enhance the performance also. Same thing here. It's like a tree, like instead of the solid it is there. Nature we are getting the inspiration, okay? And some of the applications we will see, like recent application, this is there, and we can see the KTM juke bike, everyone might have seen this, right? This structure is actually topology optimized structure. Previously it might be like some frame is there, so that they have, because KTM bikes are very heavy weight is there. So they are using the topology optimization and they reduce the weight. And this is a recent example, like 1 month back they have implemented, like this is the Ferrari race car is there, and in that they have implemented the topology optimization bracket, so that they have printed also using DMLS, they have printed this Ferrari race bike bracket. And the third one is the Royal Enfield electric vehicle is there. This I think some 5 to 6 lakh is there Indian rupees. This cost is actually recently in Delhi Auto Expo they have introduced this one. They have showcased this model. There you can see this optimization. This body is there, right? And here also it is there. This is actually completely topology optimized, so that they can reduce the weight. But I told you, right, that should serve the purpose. So it is serving the purpose. And this one is the generative design, like a furniture we are using, right? This is not a topology optimization. Generative design is there. There we can see here. Bionic design has already told you, right? See, this is the bionic design. This can be manufactured using the additive manufacturing only. Bionic design means like some organic shapes is there, right? Or like our bone has a constant cross section that we doesn't feel anything. So it will change from geometry like one point to another point. That we can observe it here. So these type of structures can be manufactured by additive manufacturing only. That is the advantage of AM. And this is also generative design. Like the main purpose of the generative design is it should serve the purpose and increase the performance also. Later they will do, like this is like a architecture model, so they might have seen for the aesthetic appearances only. They did this thing actually. But for the brackets and all those things, that is not for the aesthetic purpose. It should serve the purpose, like it should enhance the performance, like strength to weight ratio we call it as a. According to the weight, that strength should be maximized. We need to get the maximum strength to weight ratio. This is like some aesthetic purpose, they did this thing actually. So how generative design will work? Generative design or topology, and the main mode of the previous slide means both generative design and topology not the same actually. Both are different, and the algorithms for both the things are different. That is the main thing, but both the things will work on the same type. The procedure is same, algorithm is different. How generative design will work means, as you can see in the slide, I look forward in time, I saw 14 lakh some times, right? Same thing generative design will work. Generative design will take the 3D model, original 3D model, and it should do the iterations. Iterations means it should do some check it actually. Like how many steps are there, so that your objective can be convergence actually, we call it as. And we might have heard this term like optimization. First I will tell you the topology optimization. Topology means geometry, optimization means getting the best results. So getting the best geometry we are calling as a. So the meaning of the optimization is, we might have heard about this term like search engine optimization is there, SEO. Like getting the best search results. Google is good in that actually. Like out of all search engines, Google will be the good. That's why people will prefer Google. And one more thing, like during the optimization, right? Getting the best results by giving some constraints are there actually there. Constraints and finding the best objective. Suppose we might have did some Flipkart and Amazon shopping, right? There suppose I am searching for the best mobile, right? So best mobile I am searching, and what is the constraint, what is the objective is getting the best, finding the mobile. Suppose if you find the mobile and you are getting a laptop result, means that is not your objective, right? So we need to find a mobile, that is your objective. And the constraint is cost, we will constrain it. And RAM should be 8 GB RAM, 16 GB RAM, 32 GB, like that we will say. Cost means some 20 to 30,000, these are the constraints. According to that will give you the best results, right? Same thing will work on the topology optimization also. There we are getting our main objective is to reduce the weight and increase the performance. And the constraint is the stress should be, this should not be higher than your yield stress. Like we are applying a loading condition, structural I am saying, we are applying a loading conditions. Suppose you are getting in your original design, you are getting some stress of Okay, still we are taking the example and 625 megapascal as the yield stress, and in original design you are getting a stress of 300 megapascal. So the factor of safety is 2 almost for original design. So you are constraining that that should not exceed 500 megapascal, so that we can get the maximum factor of safety, right? Or 600 megapascal, that should your optimization geometry, that should not exceed the 625 megapascal. That is what we are saying. That is our constraint. Like you can compare with the Flipkart product, how we are buying the product, right? Same thing. So that is it. And how many, like after getting the so many iterations are there, that we will see here. See here, you can see here. One person is sitting on the chair here, and this is the first, like these are, I told you, right? Some designs, some features is there, some like here four designs they have given, but we can get the so many designs like that, we will get it, like hundreds of designs we will get it. Instead of hundreds of designs, this is generative design actually, forgot to say. So instead of the hundreds of design, it will, the software will automatically calculate the which is giving the best result and which is giving the like the maximum performance. We are giving the constraints, right? Whether it is satisfied the constraint or not, that thing it will give actually. So the person is sitting on the solid body. This is the body chair is there, right? In olden days, this type of designs are there. Later, how they are modifying it, that should serve the purpose like sitting. So here we can sit it, right? That should serve the purpose of the aesthetic appearances. So out of all the designs, how many possibilities we are getting means only one possibility. It is not like this design is not good for aesthetic purpose, we can use it. But we can prefer these things. How many possibilities are there means only one possibility is there. That is the last one we are getting. Means that is the converged one actually. So, and then third one is the, like we already told you about the lightweight materials, right? So, material substitution and topology optimization. And the third one is the lattice structures. And what is the meaning, what is the use of the, okay, I forgot this. As already Sir told you yesterday, right? What is the importance of the weight reduction means in aerospace, if you reduce the 1 gram of weight also, even though that will increase the fuel rate. That's why, like while going the flight, they will ask you the checking the weight of the luggage and all those things. Why? Because because of that they can increase they can load the fuel account that, so that it should serve the purpose. So if that is the use of the weight reduction, aerospace, specifically aerospace and automotive, this will be very useful, and as well as biomedical also. That we will see, biomedical one bone we will see. So that is why we are replacing a solid body with porous structures. That we call it as a lattice structures or porous structures we call it as a. And lattice structures are this is the definition of the lattice structure. Like we might have heard about the term lattice structure, right? Definition of the lattice structure means array of the unit cell. Like in BCC, the very first time we heard about the lattice structure is the body centered cubic lattice, face centered cubic lattice, simple cubic. That was already there. Based on that only we get inspired remaining things. So this is the inspiration. I told you, right, body centered cubic lattice is there and honeycomb bees is there. Honeycomb bees, this is a hexagonal lattices, and this is like a butterfly wings is there, right? There this structure we call it as a Warna structure. Means we can see here this has some uniform pattern is there, but this is like there is no uniform pattern is there. That we call it as a Warna. And this is a bone, trabecular bone. If you cut the bone on the in between, this we can see it. I mean natural bone I am saying. If we can see it, we can see this one. That we can call it as a TPMS. And the last one is the architecture. Architecture means you can see the like old palaces. You can see they might have installed this one like during the windows, and they will some grid type patterns is there, right? They will put the just for the ventilation. That we call it as a actually porous is there, right? Why they are keeping here also we can see this holes is there, right? That is like a pattern is there. That we call it as a, that hole is repeating in the all the direction. That we call it as a pattern actually. So that we can see it in the architecture and all those things. And the like Eiffel Tower is there. That is also we can see the lattice structure inspiration. And this is a geometry variation. This is a classification of the lattice structure, simple cubic, BCC. These all are like still here. Warnai stud based lattice structures. I told you in the in between, right? Middle. Sorry. Yeah. And we can see we can see this is the TPMS lattice structures. Most of the people will work on the TPMS lattice structures only. Why means the advantage of the TPMS means we can easily go for the printing and all those things. And strut there is some defective is there. The properties are good for TPMS actually with the same weight actually. So that is how gyroid and these are the 4 TPMS lattice structures are there actually. And the application, like whatever we are working, it should serve the purpose, right? These are the application in aerospace where we are using means like we already showed you, right? Topology automation, like the brackets, panels, and all these things we can use it to reduce the fuel consumption. And in biomedical, medical implants and bones, these things we can use it, lattice structures. And defense means lightweight armor systems we can use it. And energy means heat exchangers we can use it. There is a that we can in the beginning slide we have seen that heat exchangers. Why we are using the lattice structures means to reduce the flowability. Like input we are pouring a permeability, that we call it permeability. In the input we are flowing a liquid. Suppose that should be like a halo is there, it will easily dump into the bottom, right? So if we put a porous structure kind of thing, so that will pass to the pores of the heat exchanger, so that the cooling temperature get reduced from the outlet. Input we are suppose we are sending through a like some 100 degrees Celsius is there. It may reduce in the outlet, we can get it like a 50 degrees Celsius because the passing time we are increasing, right? That is how we can use it in heat exchangers. And sports we have seen that we can see the applications also in the coming slide. And sports we have seen the footwear, helmets and all these things we have seen. And the consumer products means like textures and all those things, there they can use the consumer products. And this is the application, one app we have designed, like we can see the app here. Yeah, this is the application of the lattice structures. It may go fast. Like fashion we can see, and home appliances where we can use the lattice structure. Okay. And yeah, we need to acknowledge the end of this is the project we did, like lattice structure application we can see here, branches and all those things, the text may below. Like we need to thank to the NTOP actually first of all, like because they have given the student lesson to explore the software, and we did this project actually. And this is my bio, okay. So with this, so with this brief introduction about the lattice structure and all those things, we can go for the, so any doubts on that, like any application you want to know, like so with this brief introduction about the lattice structure, we will go for the NTOP software. There what we first I will tell you the brief introduction about the NTOP, what is the use of the NTOP and what is the difference between the other software and this one. And NTOP specifically mainly designed for the lightweight structure, and how we can manufacture the lightweight structure. I will show you the design so that you will come to know what is the significance of the additive manufacturing. And people might have worked on the subtractive manufacturing and all those things, so that they will come to know whether the structure is possible to design or not also. Okay. So the main purpose of the NTOP means specifically used for the additive manufacturing purpose only, like we can design the lightweight structures, like I told you the designs and all those things, right? Application and all those things, that was designed using the NTOP only. Okay. So we will go for the like we have some, I will tell you how to generate the lattice structure and how to use it for that. Like if you want to know any further, please let me know now so that I can proceed further. Okay. Or any doubts till now? Like I will design one simple cube, I will take it, and I will tell you how to generate the lattice structure and what are the types of lattices are there. And one application also I will take it, and tensile coupon I will take it, how to generate the lattice, and two applications I will take it. Time permits, I will go over the second application, that is automotive application, and the first application is the bone, we will take it. Okay. So So what NTOP will do, I will tell you, like some traditional softwares are there, like SolidWorks and Creo is there, right? You might have know about these things, right? There what we are doing means, we have first we will design the, in SolidWorks, we will design the 3D model using the 2D sketches, right? Suppose if I ask you to draw a cube, like this water bottle is there, right? That we cannot draw it in the NTOP actually. We cannot design it in the NTOP. That we can use it in the SolidWorks sketches is there, right? First we need a sketch. Sketching we cannot do, but the 3D models we can play with the 3D models in NTOP. Okay? I mean formerly known as the Topology, now they call it as NTOP. Okay? Don't get confused. Yeah, like you will get the STL actually here in NTOP. STL. By STL I will tell you, because yeah, you can see. Okay. By STL I will tell you that I will take care of. No, actually this is the licensed version is there, but you will get the student version for 14 days I think. Yeah. No, you can import the 3D model. Any, like I will show you the what are the formats it will support. Okay. Like, but if I want to say, I can say like step file it will support, and STL it will support. Database obviously it will support. Okay. That we can import. Yeah, because I have designed in SolidWorks only. I have designed in SolidWorks only. That format only I will import it, and I will show you. Okay. That we don't actually, because I am not the supplier right now. Very good. No, I am using student version only. No, this we got the license from the from them only. So right now it is going on. For this only we took it actually. Student version is there. There is a student version for 14 days. It is there actually. Yeah, just to explore actually. That you need to request them actually. In NTOP website there is a like get a student version for 14 days. It is there actually. Yeah, one more thing is like this is actually cloud based one. Like you need to connect with the internet. Like suppose if you are not using the for some 10 days or something, it will ask you to log in again, because they will take the data what you, whether you are using the for the right purpose or not. So yeah, where we are, yeah. Is that okay? So is the dark mode okay? For you it is okay, right? Otherwise I can change the mode to light mode. Fine, right? Okay. Yeah, here we are, yeah. Yeah, what we are doing in the conventional design software means we will take a 2D sketch. Suppose I told you, right, if you want to draw a water bottle or something, in NTOP we cannot do, but in SolidWorks we can do, and we can extend that model. Extend that model means we can take that 3D model and we can use it to reduce the weight and to add the texture and all those things. Texture means something like some different patterns is there, right? Customization. That we can do it in NTOP. So 3D models means basic 3D model we can do, like cube, cylinder, these things we can do, cone shape, these things we can do, but we cannot do a 2D sketches and all those things. That we can do it in the SolidWorks. So we need to know the other CAD software, SolidWorks, KTF, Fusion 360 or Creo, anything. Then we can import the 3D model in here. Okay, that I will show you. First I will tell you I will explore the simple cube. I will take it not from here only. I told you, right, simple cubic designs we can do. Okay, so this is the lattices, we can go with it, and you can see some text will automatically appear, so that you will come to know, and you can, if you want to know, you can take the help. I will tell you how to take. See here it is there, right? You can take like that. Like what is the meaning of that? I mean, like provide the input and box, these things we need to input. Volume means, and one more thing, the good thing about the NTOP I will tell you, like for my personal experience I will say, like we have designed actually some BCC, FCC lattice structure in SolidWorks long back before the NTOP. The problem with the FCC designing the FCC structure means lattice means repetition of the unit cell. Like you have seen the Rubik's cube, right? Rubik's cube 3 by 3 by 3 by 3 is there, right? Or some 6 by 6 can repeat in the all direction. But in SolidWorks there is a problem with that, means once we go for the repetition of all those things, it will extend the memory, and so that your system will get hang. That we already faced that by designing the units and all that. But here it will take very like milliseconds. It will give you the, it will generate the design, like one we have seen the lattice structure and all those things. How it will generate the design means nowadays, I mean this is also maybe SolidWorks may use. They are using the implicit modeling. Implicit modeling can give you the faster results. So that we will see. And means implicit modeling means implicit bodies they are using. Okay. So rectangular volume lattice we took. If you want to go here, or you can search it here. Add block is there, right? This we can use it as a search engine. I usually prefer this one, so that I can search it whatever I want. Okay. So lattice I put. So volume means I told you like 3D model. Since we didn't import anything, so I can take it from the top only. That volume I can take it as a cube model or cylinder or anything. I will take it as a cube. Okay. So I will search it here. Cube. See, we are getting a cube, right? So I will take the cube size as a 30 mm by 30 mm by 30 mm or 50 mm by 50 mm by 50 mm. Okay. Okay. And the unit cell. Unit cell means I told you that there are three types of unit cells are there. One is like a 2D lattices is there, and the other is like a PDMS. PDMS means strictly periodic minimal surfaces, and there is some mathematical things are there. I don't want to go for that. Like I call it as a minimal surfaces is the PDMS. That is a type of unit generally go to that. And other is like a strut-based lattice. Strut-based lattice means you are seeing this PVC and all those. PDMS where there is a bone clearing or bone clearing, like implants is there, right? We are seeing there is bone is there. That bone implant we are seeing that there is the PDMS lattice. So unit cells, three type of unit cells are there. And in Endo they call it as they divide it into two. But in our research purpose we have divided into three. I showed you in the video, right? In Endo they have divided into two types. One is like a graph and the other is like a TPM. Graph means like a line diagram. Using the line diagram it will generate the lattice structure. Okay, I will show you. See, if you don't know, like if you are a beginner in the Endo, like since I know this software, right? So I know what input I should give. So if you are beginner in the Endo, what to do means you just press on the double click on it. Empty is there, right? We need whichever the optional is there, that you no need to keep, because that is optional. Empty means you should keep so that to get the design. Just press on the double tap on it, double click, so that it will give you the available options. These are the options you can use. So I will use the graph unit cell. I will use the PPM unit cell. This option you can show you. First I will use the graph unit cell and I will show you. Okay. So again empty is there, and this is the ribbon is there, so that we can see the available options. See, these are the types of lattices are there. It's strut based actually. Okay. And hexagon and honeycomb is there, that is 2D. They have combined merged with the graph. So these are the types of lattices. BCC I told you that. First we will see the BCC, how it will generate the BCC. And something like unit cell size I have given. Unit cube I told you that. Some the standard is there. That is together that we call it as unit cell. That has some basic size is there, right? That we are taking here. And 5 by 5 by 5 mm I am taking. So the deepest thing is like I am taking a 6 mm cube, and in that 5 by 5 by 5 unit cell is like a 5 by 5 by unit cell is there. So this is cube is there, right? In one direction how many unit cells will come? Yeah, 5 unit cells. And the other direction, by direction 10. By direction 10. So total how many unit cells will be there in the lattice? 10 into 10 into 10. Right? 1000 will come, right? So 1000 unit cells are there in the 50 mm lattice. So by combining all the unit cells, we call it as a lattice structure. So I will show you the how BCC will structure will look. See, you can see this is a graph view, means line diagram. I told you, right? And if you want to go implicitly, you can see. See, this is how BCC will look. I will reduce the thickness. Okay. And if you want to show the FC simple cube, it means this is how it will look. Okay, and the FCC. This is FCC, right? Face centered. All faces are centered. And diamond. Okay. And there is some controls are there. Controls I am not saying because these controls we can customize it. Like suppose if you are using this SolidWorks or something, according to that you can customize it. I will show you that. Camera control setting. Suppose if I am in SolidWorks, NX Creo is there. Whichever software you are familiar, you can customize the control settings. Since I am familiar with SolidWorks, so I will use this. So that the remaining zoom in, zoom out, everything will be same. Okay. So this is the diamond. And one 2D lattice we will see. Hexagonal honeycomb. I showed you in the inspiration of the honeycomb B, right? Implicit view. See, previously we have seen that the direction is changing, but it is like a 2D is there, like some pattern is there, we are extruding. There is no 3D. 3D means simply extruding the 2D pattern. But in lattice, in BDC, this is not like this, right? That is the difference why we are calling this as a 2D lattice. And 3D lattice means PPMS, surface, all these things are 3D lattice. So that's why we are calling this as a 2D lattice. So we can go with it. And one good thing about this is re-entrant. This actually, anyone heard about this term re-entrant? There's some specific properties there actually. Direction, if you try, you will get the negative Poisson's ratio. Okay, this only we can extrude, then we will see this. So thickness I will keep it as a, this is empty, see, not optional, so we need to keep it. So thickness I will keep this as a 1 mm so that we can see. See, this is loading. If you want to see the clear view means,
you can see the rendering quality also you can see, but always prefer low quality. It depends on your graphic card and all those things also. So we prefer the low quality. By saving the name, you can take the HD directly. Like the cube which I took from the NTOP only, right? That these simple designs are available in the NTOP. Suppose if you want some tensile component, we cannot draw in NTOP. We need to took the advantage of the 3D CAD software like Creo, Fusion 360, NXV, whichever you are familiar, that we can take. You can take, and you can. The universal file format means step file. Like some softwares, like every software can accept the step file actually. Like why we are using the step file? Why we are calling as a universal file format? Any idea? That we call it as a universal file. STL also, for step file we call it as a universal file format. That. Yeah. 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 Yeah, I will tell you the example. Like suppose you have designed one model in the SolidWorks file format, and you might have sent to your customer in the. You might have sent the 3D model to your customer. Like I mean, as an industrial person, I'm saying, you need to send to your show the 3D model to your customer. Like if you send it in STL PRT file, and the problem with that, he should have the SolidWorks format. Suppose he might have had the Creo also there. He is having a like 3D model software is there, or some other online resource is there. In step files can open in online resources, some online resources are there. The STL will open. STL viewer is there, in online resource also we can see. We know it. And nowadays we are getting a 3D viewer also in Microsoft. So tensile ending, see here you can see here is I think one person asked the available file formats, right? This is the available file formats, it can accept it. You can see STL is there and OBJ is there. What is it? As already Sir told you yesterday, OBJ means like the texture we can see wavefront object. Okay. Yes, step is there, inventor and SolidWorks, NX, Creo, everything is there, right? These are the file formats NTOP can accept, and in future this may add actually. So our file format is already there, so I will keep the all compatible files. So SLDPIT is there and step file is there. So we can take that as a, you can take the step file or SLDPIT. Both are same only. I mean here. Okay, I will take this step. Okay. See, my intention is to, as I already told you, right, lattice structures. If you are doing, previously we have designed the, how we can say, like, you might have heard that design space and non-design space means. What is the meaning of design space? I will tell you. Design space means your intention where you want to modify the design. That we call it as a design. And where your design won't change, that should be keep it as a original. That we call it as a non-design. Here what we are doing means, this is the tensile specimen, right? Here in between, in the middle only, suppose if I am designing my model with the 3D SolidWorks means, I think this is actually 3 models actually. See, you can see. seen here, 3 bodies is there. So left, middle, right. Okay. These 3 bodies I have divided. Why I have divided means my intention is to keep it on the middle body only. So I have divided. Yeah, you can suppose you have the extension. Bone is also there. Right? Bone also in between only I need to put the add. That we can see how to do this also. First we will take a similar example of the bone also. First we will see this one. What sir? Like in abacus also we can do, or in entop also we can do structure like suppose we are keeping this one actually, and in between we are applying the lattice, right? So one end is fixed and the other end we are applying a load actually. So no, we can combine it. We can combine it. I told you right. Like suppose before doing the simulation also we are going for the printing, right? If the parts are separated, we cannot get the correct print. So we are combining the 3 bodies actually. So for that we are using the Boolean union operation. And top it is with Boolean union subtraction. I will show you. Yeah, it is there actually. Like we need to define that this is design space and this is not design space. In SolidWorks I have defined this one. Because this option we cannot do. This similar example is there for bone also, where we can define how to do this. Okay. Yeah, but depends on that you need to take the you need to take the decision. If you want to take the close the body, then you don't need to define the design and not design. Best example I will tell you. Where what is the meaning of design and non design? Bracket is there, right? Yeah, you might have had it. That is exactly the back on the reduction. So suppose what is the meaning of design and non design? Suppose I will tell you. Like sir has already told some bracket is there, right? Brackets and holes are there. Holes and everything. Why means one hole can be fixed and the other like this. Fixed means both the joints we are applying, right? That is fixed we call it. Suppose if you are applying a hole on it, on the lattice body, we cannot keep the threads and all those things, right? So that we call it as a design space. Whatever the holes and bolted joints is there, that we call it as a non-design space. Means our lattice should not touch there. That we call it as a non-design space. Usually these terminologies and we need to do the topology optimization. As well as the lattice also we can use. We can add the space. I can add the space. In lattice space also we can use because lattice topology optimization how it is remove the design space. Design space is there, remove the material if we didn't define the design and non-design space. Non-design space means that will remove the material in the space is design space. Like it will avoid the non-design space voltage joint those things. Okay. Same thing also lattice also is there. One example is there plate cover I will show you. Where you will get to know. So this is the lattice body, and see I already convert into implicit body. How to do this means just press on the double press it, convert into cat body to implicit body. Okay. So these 3 bodies are there. I already rename it as a left, right and middle. Okay. Now I won't combine because my aim is not completed. Aim is completed means I need to apply the lattice immediately. After completing my objective, then only I can combine the 3 bodies. So left is this one. This I can't apply the lattice body, right? I don't want to apply the lattice body. And then this is right. Here also I don't want to apply the lattice, okay? This is middle. My intention is to keep it here only. So what I took means here I took, see. See, I apply a lattice here. Now we can see. Like this it will come actually. control is there, right? I will keep this here. See, this is called, we call it as a pores. So we have, I told you that some fluid application we are using the, like if you pour a fluid or something, it will come out of the liquid through this pores only. Mainly the thing is permeability also we can calculate using these lattices also. This distance between pores we call it as a 2 mmc. Actually each unit cell, you can see it here. Yeah, yeah. Yeah, mainly specifically TPM of characteristics are for character. If you ask specifically the gyroid is a one step. Here we are using the gyroid only. I will show you the gyroid. It depends on the, yeah, it depends on the curvature also. I will show you here. Yeah, mean surface is like TPMS means the zero mean surface is there. So strictly periodic minimum surface is there. That structure itself we call it as a TPMS means there is a zero curvature is there. So the support can be less than 45 degrees so that we can without the support. We have tested also these things also. Where we are 3D printed using SL and so this is a structure, our middle part is getting like this, and you can see left body, right body, but now this is not even combined, right? So I applied a Boolean union. You can see here Boolean union. See, I told you right, and top like after completing our retention, we need to combine the three bodies. Here I combined, here you can see. This is lattice body, and the left body, right body, you can see here. Okay? So that we will get like this. See, now the dash line is, previously we have seen the dash line, right? See, now once I combine this, that is gone, right? So we have combined the bodies. So we can mesh the 3D body and like why SCL means this is like a intricate geometries are there, right? See, if I want to capture this sharp curvature of geometry, I need to use the tessellations only. Like some solid body, some triangle, like some solid object, original bodies that we can capture in the IGSR step format. But to capture the intricate, like very precise geometries means we are using the tessellations only. Okay? Why tessellation? Why triangle? Any idea? Like why triangle? Why not square or something? Why can't we capture with the square? Why triangle? Why STL is called it as a tessellation? Yeah. To get a closed surface, triangle is the minimum number of lines we are getting. Suppose I have given the two lines, right? You can draw like this, but there is one gap is there. You can close it like this. So to minimum number of lines to close a surface means 3. If you draw a square means I can draw one more line. I can say the triangle. And if you draw one more line, it will become a triangle only. Whatever the number of lines you can draw, that will increase the accuracy. Triangle. That's why we call it. We are using a translation triangle. And in 3D models also for complex structures also, during the analysis, like in industries, they will prefer the tetrahedron instead of the hexagon to get the correct capture. But the problem with the tetrahedron is it will increase the element sizes. That's why STL file size will be very high. Tessellations will get increased. So they will use the tessellations. If it is increasing the element size means obviously the simulation time also will get increased. once we combine this one, this is how we are getting a 3D model, and you can export into, you can mesh the 3D body. I will show, but I can't mesh from implicit body. This is once we, yeah, this is the one I told you, the implicit body, right? Whatever the like universal whatever the bodies that are generated in the entop, that we call it as the implicit body. Here also there is no CAD body or something. CAD body means you can touch the faces here. Here you can see this is the, I will show you. See, I can touch the faces, right? I can touch the lines, right? I can touch the points, right? And this is implicit body. Suppose I want to convert this into CAD body, I can convert into CAD body, create CAD body variable. But the problem with here means I can't able to touch it, because that can be converted into the implicit body, that can be taken as a one body only. So once we combine the Boolean union, then we can mesh the implicit body. And the how to, like suppose if you are a beginner in the entop means, how to learn this means, once our aim is completed, then we need to convert into STL body. And I told you, right, implicit body, you can just search it here. We need to do mesh, right? Available options will come. Whether is it a CAD body? No, it is not a CAD body, right? Implicit body. So implicit body DC is there. One more thing, this is recently they have added DC. Why they have added means just to, I mean, people they have complained actually, like I will say one thing, I can't mesh, but I will say one thing. See, we are using a meshed body, right? The thing is, I told you, STL we are using for the like detailed, intricate detailing STL triangles. Very less size triangles we are using for the intricate geometry. But see here, this is not an intricate geometry. This is completely solid, right? We don't need that much of precise tessellations, right? So if you are going with the mesh from implicit body, it will take it everything as the same type of tessellation size. But if you go with the mesh from DC, it will automatically calculate. Like this software, like this is a original body, so here we can capture with the two lines of diagram, this one, and here it will increase the tessellation, so that your file size get reduced if tessellations get reduced. So we can prefer the mesh from DC or mesh from implicit body DC also. So this one. So once we completed this one, and yeah, why I am saying means how to identify the, there is a shortcut. You can see the icons here. What does it mean? Means there are two types of entop is all about Boolean union and understanding also. Like you cannot get that tutorial software. Tutorial software or very advanced software. So once you understand, you can play with the entop. So you can see the implicit body is there. That means I am touching here, right? Means it is asking that you need to put it in the implicit body, not CAD body or something. Or otherwise, there is one more term is there. I told you, right? Double click on it. It will show you the available options. For me, I need to keep this body, implicit body 5. So I will click on it. 5 is there, so I can put it. Or otherwise, one more method is that every time it won't work. One more method is the logo icons. You can see. You can see here, right? Icon. The same type of icon where it is there, that type of bodies it will accept actually. See here also this icon is there, right? So this will accept, and here also this icon is there. This will accept like that. See, right? Right, like that. And the tolerance and all those things, mesh size and all those things. Okay? Like if you have a big system, you can use you can run the meshing in my system and in this system. So we need to create it with this, right? So we need to get the 3D models STL file for it. But if you keep the very low tolerance means your STL file size will get increased. And the build time will while importing the build software also, processing time will get increased. But if you are thinking about the precise geometry means go with the less 0.2 mm or something, and it depends on the this size also. Suppose the thickness is a 2 mm means we can go with the 0.3 mm. The thickness, the wall thickness is there, right? Yeah, suppose that is a 0.5 mm something or means we can go with the 0.1 mm precise. So So we cannot capture the 0.5 mm thickness with the 0.5 mm tolerance, right? So that is why. So that is one thing we can do. Tensile we can do. Any doubt till here? You understand, right? So first what we are doing is we have imported the 3D model. We have already designed in SolidWorks. If you want to show, I will show. This is the 3D model we took, and we have drawn the lines here. Separate I have extruded. See, first I have extruded this one. 3 bodies I have extruded, and I didn't combine actually. See, there is option called merge result, right? If I merge result, what will happen? We'll see. See, 2 bodies. 3 can change to 2. Merge result. See, 3 can change it to 1. 2 can change it to 1. Okay? Or otherwise, combine this one. Again, only one body we are getting. Suppose if you are getting this body, you can do it, still you can do in the end top also. That example we can see it for the bones. Why? Because why can't we do it in the SolidWorks? Means bone is a STL file geometry, because that is a 3D scanned geometry, right? So we cannot design the bone patient to patient. We can scan the 3D model and we can get it in the STL file tessellation format. So bone is a STL file format. So we can play in NTOP only. NTOP available option. How to cut the geometry, how to define the design space, non-design space. Okay. Yeah, we can do it. Now, yeah, in bone there is a gradient only, because we need to vary the properties, like the Young's modulus is there, right? Yeah, we can define. We already did this. We can define means from this point is there, right? This point is there, right? Suppose here one thickness you need, and here one, like some 1 mm thickness you need, and here you need 0.5 thickness something you need. Like that it should vary 1 to 0.5 or 0.5 to 1, it should vary. That we call it as a gradient, so that pore size also get reduced. That we can define actually. Yeah, features are available, but the thing is, NTOP there is no feature like uniform lattice or gradient. We need to do that one actually by using some other option is there. Till now whatever I have designed, that is uniform lattices. Uniform lattices means the thickness is uniform, pore size is uniform, every property is uniform. Gradient means from point to point it will change, right? The thickness and the property, so the properties, thickness, everything will change actually. That we call, that's why we call it as a gradient. That feature is there available in NTOP. That is called ramp. It is there. There we can do like. Wait, I just want to show something. As Sarah asked about that one, right? I will show. This I have designed here. See, you can see bone uniform is there, and the gradient type A, type B, something I have defined. Like suppose type A means here you can see in the geometry. See, here you can see the thickness is uniform. You can see here the pore size and thickness is uniform. But here you can see the thickness is very less. Here once we go through here, the thickness is increasing, right? That we call it as a gradient. See how much thickness is here and how much thickness is here, right? And this is like type B, and from center to till the end it is. Oh, is it? Okay. Now is it okay? Okay, okay. Thank you for that. Okay. So now you can see from center to here, this is changing. Like suppose if you want to explore about the more about the lattice and all those things, means you can go through here, and I mean since I have designed this, some of the application, yeah, I have given this. Yeah, like some of the one which I showed you in the animation video right, apps, I told you app right, these things are there actually. We have designed, we can download it, and some of the structures which I took it in the NTOP only, this thing, texture I told you right, this thing we can do, and medical applications, how we are using this lattice and all those things, that you can find it actually. That is how that gradient is possible actually. I showed you this one right. This is actually gradient, type A, type B, and this is actually uniform. Uniform means same thickness is there. So this is how we can, like one example is that we took the we have designed the 3D lattice structure, like just to do the compression and all those things from the implicit body. And the other example is the tensile body. Since we can't able to draw the tensile body in NTOP, so we have designed in the software, and we took it from the CAD software. We took it actually we imported into the NTOP, and we have applied the lattice here, and we can combine the three bodies so that convert into a single body, and mesh it and import into STL file. Okay, export into STL file. Till now any doubt is there? Gradient we have completed, like what is the meaning of the gradient? Any doubt? Nothing is there. Then we can proceed for the other example. Two example we have completed. One is like a cube lattice, and the other example is the tensile, and the next one we can go for the bone. Yeah, that is ASTM E8 standard. The one which I used to my study also. Particularly what you are asking, lattice structures or tensile testing lattice structures? Yeah, why I told you right, because that gauge length only, our intention is to go for the gauge length portion only, right? Even though if you are design, that will go into the gripping portions. The left side and right side will get into the gripping portion. So how it is failing, we need to see in the gauge length portion, right? That also we can do. Okay. Yeah, yeah, I will tell you. Like the failure you are asking, like or the cup and cone. If it is like a cylindrical cup and cone, and if it is like a shear failure, something we can see like this, right? The thing is, the failure for the different structures, the failure is different. That's why in the video I have shown you, right, the geometry variation is different for different lattice structure. So the properties is also different actually. The properties and the failure is also different. And we did means one of my co-scholar did on this thing, tensile. My work is on the compression, so I did on the compression and the application point of view. Whatever the slides I have shown you, right, topology optimization, generative design, that I did actually. So this also we can do, like the failure and this thing is there, right, that you cannot expect a shear failure or something. That may fail, some brittle failure also will happen. And if you go for the strut based lattice structure, okay. And if you go for the some other structures, means the failure, strut based lattice structure means the failure can occur in the, like the junction points is there, right? Why we are getting the junction point means because of the sharp corners is there. Stress concentration, we might have heard the name, right? Because of the sharp corner, stress will be concentrated there. So the failure can start from there only, sharp corners. So to avoid the sharp corners, designers how they are thinking that designers how they are thinking means they have applied a fillets at the sharp corners. Long back previously they have used a strut base, later they have modified into sharp corners because they are getting a failure at the sharp corner. So they have applied a fillets at the sharp corner. Still they are getting a failure, they are getting less properties. So they have opted the TPMS lattice structures. So to improve the properties, and we are not getting, there is no sharp corners in the TPMS car because that is the curvature geometry is there, right? One point to one point it will change it actually. There is no standardization, sir. It depends on your requirement actually. You can increase, that is not an issue. Wait, I will tell you one example here. What is that? If you increase the unit cell, then support structure, like the pores is there, right? The curvature is there, right? Anyway, we are getting a hole only, right? This much of hole we can print, but if you increase the hole size, for SLM I know because I am working on the SLM and I have referred the papers. There is Muscari, one guy here recently, Muscari. He worked on this actually. What is the best size for the lattice structures to print? And he told that 5 mm is a good size to print without support structures. Later we can print without support structures, but the problem is that it will fail. The deformation will occur. So without support structure, 5 mm unit cell size we can print. For SLM I am saying. For FDM it can increase beyond the 5 mm. And in our design we used actually 21 mm cube is already there in the document. 21 mm cube lattice and 3 mm unit cell size. That is the use. Because if you the problem is this means like what I do the problem is since we are using a metal structure and I cannot go test it with a 100 km material because that is going beyond the that is taking unit cells are there. There is a again it is going generating like testing media and doing testing media like this. If you take it with a 150. Saying you have to. Now is it okay? Is okay? Okay. Yeah, where we are? Yeah, testing. So like I am using a the testing properties will depend as already sir asked, right? Like if I am going with the 5 mm or something, the thinking what will change means porosity will change actually. Pore size is increasing means suppose in the okay, I will show you the weight saving something, the one which we are interested. How much weight is saving with this design? I will show you. Left, middle, right, see with this we are increasing at 10 almost 9% of weight saving means 91% of material is presented here. Suppose one more thing, one more design I will show you, that bone I will show you, there you will get the clear understanding of the porosity and all those things. 9% of material is there means 91% material there means 9% porous is there, okay.
Here you can see the number. We'll do this. Yeah. Break, huh? Okay, we can go for break, then we can go for the remaining things, and the 3D expert also we can do. If any doubt is there, I will be here, you can ask. Any doubt you want to see. లేదు ఇదే బెటర్ అదే ఇదే బెటర్లే అక్కడ ఎవరు ఉన్నారా ఆపరేట్ చేసి మళ్ళీ ఏదైనా ప్రాబ్లం అయితే అందుకే ఎవరో ఒకరు ఉండండి, ఫోన్ చేయొచ్చు. అక్కడ ఏదైనా ప్రాబ్లం అయితే ఎవరో ఒకరు ఉండాలి, మరి పరిగెడతారు సిస్టమ్ కనెక్ట్ అవ్వకపోయినా నేను చెప్పడానికి. నువ్వు వెళ్ళలేకపోతే నీకు తెలుసు కాబట్టి నీకు ఫోన్ చేస్తా, నేను చేసుకుంటా. Shall we start? Am I audible? It is there. You can get it. Okay, you might not know. Okay, there are some websites are there, like to download the 3D models, GrabCAD, Thingiverse, some websites are there. It is there in my app also. Okay. Yeah, I downloaded from the Thingiverse, I think. Yeah, Thingiverse. 3D printed models you can get it. Bone, this I have downloaded, and I told you right, for bone and all those things, that is like a scanned models. We can get the tessellations. You can see there is no square type of thing here. That's why I zoomed it here. All are like a triangles only. You cannot find a square type here. Okay. Thing THINGIVERS. Yeah. Yeah, sure. This one, bone. The models which I told you right, you can get it from my website, like this one. So the model which I told you right, like I can't say every model how I designed. I can't go beneath the layer, so tip of the iceberg I can give, but the 3D models you can download it. This is the one you can download it, okay? And Thingiverse, this is the one bone you can get it here. See, this is the one bone you can use any bone. There only I get it. And Thingiverse can download only STL files. Remember that. There is no CAD model. GrabCAD means, as the name itself, you can get the any CAD models. Whoever the person, like the designer uploaded, suppose if I am the designer, I uploaded the step files, STL files, and if I design in the SolidWorks format, I can upload the SolidWorks format, like that. That's all. That website can take it. Okay. So this is the meshed body. So tessellation get confused. So like this it will come, right? So what my objective is to, I need to apply a lattice here. In between I need to apply the lattice. So previously the same thing here also there. Tensile body is there, right? Left, right, middle. Same thing. But this is the STL body. Previously we have designed the CAD body and we have separated in the CAD software itself. But here in NTOP, this is the STL body, and we cannot do the separation in the SolidWorks or CAD software. So we are using the NTOP here. How to do that means, first we will convert into, and I told you right, in NTOP we can play with the implicit body. Once we convert into implicit body, then only we can do whatever the operations, Boolean union or some cutting, subtraction, these things. So first we need to convert into implicit body. Okay. There is an option called implicit. See, this is a meshed body, right? So implicit body from mesh. Okay. So I will import this one, I will drag this one. You can see here, I told you right, icon, globe, network symbol, globe symbol is there, here also globe symbol is there. So this will accept, or otherwise double click on it, available options it will show, mesh_1 name, okay. You can get this one. See, it converted into implicit body. See, previously our body is like this, now our body is like this, okay. So now we can do the whatever the operations we can do now, okay. So first what I will do means I will separate into two bodies, okay. Like this is left, right, and middle portion like this it is there actually. It is there like this, and I need to extract the middle body. So what I will do means I will take a planes and I will cut it. With respect to that plane I will cut it. Like this I will take a plane, this is the bone is there, right. Like this some like bread is there and knife is there. We are slicing into like this, we are slicing means it will separate like this, right. Same thing. Means plane I am taking. Your plane normal is there, I am taking like this. I will show you. So for what is I told you, right, entropy is like if you understand the Boolean union, subtract and interaction, then you can understand the entropy. So subtract we will see. Then union we already seen, combining the three separate bodies. Three separate body means that should have a contact. Then only the meaning of the union is had a purpose, right. If the one body is here and the other body is here, means there is no purpose of combining actually, okay. That should have some contact. So once we convert into implicit body, then we can separate the body and we can extract the middle portion. How we can do means, so Boolean subtract, my primary body is this one only. In this only I need to do the operations, right. So that is my primary body. See, icons are there. I can drag it and I can place it here, okay. Remaining blend radius I am not exploring, you can get it in the help also. I will keep this as the same. So what I will do means I will subtract with the plane. So the subtraction body is the plane. This is the body is there, right. One body is there and I am applying a subtraction here with respect to this plane. So this body can separate. How? From primary body, okay. So I will take plane from normal is there, okay. See, your plane is here and this is the implicit body and my plane is here. So I need to drag this plane, okay. You can keep it, okay. We will see how it cut it. See, like this we are getting, right. But I will perform in a one single stroke. I will extract the 3D body. I mean, okay, we will see. So one more plane I will take it. This is the implicit body, right. See, this is removed and I need to remove from this side also, right. So one more plane we will take it, plane from normal, or otherwise I will copy the same plane, Control C, Control V, and this one I will see this symbol is there, right. That is the toggle visibility, okay. So this plane I will drag this here, so I will be here, okay. Now we will see how it can. Again we are getting this one, but we are getting the same direction of the plane. See, this plane is in the same direction, this plane is in the same direction, right. So I will change the direction, one direction I can change it. This I will keep -1, I will see. Oh, both the planes are same, okay. Okay. minus 1 plus 1. Yeah, see I am getting the middle portion, right? See, previously this is the one and I am applying my body here. I am applying, my intention is here only. So the remaining portions are the, this is the design space, remaining portions are the non-design space. I don't want to apply the lattice there. So I separated here. So you might have a doubt, we can do the same operation in the SolidWorks or other software also. But the problem is, SolidWorks means STL files, we cannot play the STL files, right? So NTOP or Magix, like Mimics, these things only STL file can support. There we can separate the bodies. But I am using the NTOP and I am separating the two bodies, okay? So I will apply the lattice. First what I will do means, this body is there, but the other two bodies I don't have, right? So initial body is there. Again I will take the subtraction from this, okay? You understand, right? Suppose this original body, from this original body, if I separate this body, I can get the remaining two portions, right? I will rename this one bone under bone lattice. Otherwise, design space, right? So again Boolean subtract. So my primary body is my original bone. I will take this name as a bone, original. Now just to identify easily, I am renaming this one. So original, if I type bone original, and the subtracted body is the bone design, okay? See, I am getting this one, right? So this is my non-design. Yeah, this is my non-design body, means my lattice won't touch there, okay? Non-design, okay? So I will apply the lattice to the bone design body, this one, okay? Again same thing. See, I already applied here, you can see here. Okay, I will apply once. Let's see. So my volume is that implicit body. Volume obviously implicit body I should apply. So what is the implicit body means? This one. The design body I need to apply. So I will drag it, double press on it so that you will get the available options. So I will use the wall TPMS unit cell. This time we can use the diamond. I will increase the unit cell size. Like 3 mm. Yeah. So I will further increase the unit cell size to get to see the pores. Okay. This each wall is there, right? That is of 3 mm thickness. Okay. So this one is there and this one is there. Now again same thing, same operation. We have completed this tensile operation only. Again once we are getting thing, we can combine the two bodies, right? So Boolean union. There is some one part is there, intersect is there. Intersect means common portion we will get it, okay? So two bodies we need to combine, okay? See, we have combined the two bodies. And if you want to extend this further, you can increase the plane. Plane, this is there, right? Here planes is there, right? Here one plane is there, here one plane is there, right? See, we are cutting like this, right? we are applying a plane like this, your plane perpendicular is there and we are moving like this, okay. You can increase the further so that you will get the bone lattice portion is there. I have randomly I put the length and all those things. Like this you will get the bone to the lattice body, okay. The same type of design is already available there, you can get it here. Gradient also it is there. So clear? Then if you are clear, then we can go for the engineering component, that is brake pedal. Any doubts is there? Yeah, forgot. Well, like weight saving? Yeah, I forgot. I will do. Yeah, see weight saving is there, right? That is important finally because, so I will rename this as a bone with lattice. Now why I am renaming this one means later like wait. I will show you one thing. See. Yeah, actually this project is there, lattice structure applications is there. There are like some hundreds of designs is there in the file, like it is of 2 GB file is there, hundreds of designs are there. Like if I didn't rename anything means implicit body 1 means it will go like implicit body till 1000 or something. So each one I have renamed the separate file, like some French's something is there, right? So French's body, French's original, French's lattice, like that I need to rename. If I didn't rename means it will go, you will get the confusion while applying the so many operations on these things. That's why I'm like it is a good practice to rename it actually, okay? So bone with lattice, that is a lightweighted body, right? Bone with lattice. Okay, and the original body is that bone original, I think. Yeah, bone original. Okay. Yeah. In topology actually use the topology optimization, but Fusion 360 will use the generative design. The thing is like right now I am learning that, so I can say this thing. It will use the cloud credits like in AI is there, right? AI, if you want to generate image means we need a prompt. We need to buy the prompts, right? For it is open secret. Like for educational one, if you are using for the educational purpose, you can give the Gmail also. You will get the unlimited credits actually to use the generate design. After 2019, I think they have adapted this one to give the education license unlimited credits. We can use the generative design for Fusion 360, and what I like as per my information, only Fusion 360 is the one who is using the generative design. Remaining all other software like ANSYS, Abacus and Entop are using the topology optimization only. Only Fusion 360 is using both generative as well as topology optimization. Generative design in Fusion 360, like I am using student version, so I don't know whether that module is there or not, but generative design is there in Fusion 360. It will remove the material, unnecessary material it will remove. Yeah. Yeah, like it, yeah, branch or something like bow. Then that is not there in actually here. That you can go for the entopology. I told you right, like MS lattice is there and entopology is there. These are the two one, but in entopology you can play with the surfaces and all those things. In that you can do it in entopology. Like the simulation we can do. Like we can topology optimization will take the load simulation actually. Yeah, as well as generative design also will take the The basic idea of generative and topology optimization is that we need to get the best result. By taking the, it will take the objective, your objective is to get the good result by maximizing the strength and reduce the weight. And the constraint is that it should not exceed the, this much of, it should not remove this material, passive region, non-passive region like the design space, non-design space. And it should not exceed this much of stress that we can, that these are the constraints actually. According to that, it will generate the design or it will optimize the body. That we call it topology optimization. Algorithms are different, both the things. There, generally no actually. That we can do actually. Yeah, after topology optimization, we can incorporate the lattice. I mean, yeah, like I don't know how to say, like it is like related to my work only. Like that only I did actually. Like after incorporating the, after completing the topology optimization, like previously I showed you, right, weight reduction method. These are the some weight reduction methods is there, right? Based on that, I wrote a one paper. Like I took a one bracket is there, and I applied the topology optimization, and I applied the lattice structures, and I combined both topology optimization as well as the lattice structures also. These things I did, and you asked the gradient, right? There also I did actually both uniform as well as the gradient lattice structures I applied. Like I just want to explore the how much is the potentiality of these methods are there and how much weight reduce using these methods. Yeah. 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 That, yeah, that is the problem. And the simulation part you can do the entop, but the problem is that we cannot trust the entop results, so we are using the abacus explicit analysis. There we did, and I used abacus implicit analysis, static analysis I did actually, not dynamic. Dynamic also, dynamic you can see the real-time data, these things we can see. Abacus is good to go for the entop parts to do the simulation. No. But we can apply the like lattice to the topology optimized body. But generative plus lattice structure, it is not there actually. It is not there. I understand. And the thing is, only Fusion 360 have the ability to do the generative designs because it will work on the AI based designs. So it will take the cloud credits and all those things. And education license, it is unlimited. You can explore it if you are applying the education license. And remaining other software is the topology optimization only, as per my information. So that is how you can design the 3D model. And if you are extending this operation, you can go with the, you can increase the lattice length and all those things. And the density you can see 13 point, like weight saving is 14%. And if you want to increase the weight saving, what to do? If you want to increase the weight saving, what to do? Suppose, okay, this is the basic actually. How to increase more porosity? Reduce the thickness. If I reduce the thickness, then the component will be lighter, right? So porosity pores will be more, right? Or otherwise increase the lattice size, like some 50 mm cube is there. I am applying 5 by 5 by 5 means how many things I am getting? 10 into 10 into 1000. Suppose if I am applying 10 into 10 into means 5, 225 will get it. 225 unit cells I will get it, right? So unit cell size get reduced, so the lattice density will get reduced, right? That is how. I mean, these are the parameters you can do the optimization, like how to increase the porosity and all those things. If someone asks means increase the unit cell size, means decrease the number of unit cell size, okay? And the decrease the thickness also, there, that also we can do, okay? So that is how we can do the bone. And there is one more option is there, engineering brake pedal is there. Okay, we will export it. Okay. Yeah. See again, this also like I told you, right, design space and non-design space is there, right? This is the best example. You can see it here. I will tell you, some holes are there here, but I cannot able to define the design space and I cannot able to cut it actually. That we can do it in NTOP easily. We will see. And I already separated this body. My intention is to apply the lattice here. So I separated this body in the SolidWorks only. See, in this body I don't want to apply the outer body lattice, right? So I want to apply the boundary region. This boundary I have confined, so I will apply the boundary. I have defined the boundary, I will apply the lattice here, okay? So first what I will do means, I will take this into new section. Close this, okay? First I will convert this into the implicit body, okay? I will rename this one break. This is your design space, okay? And this is, and how to convert into implicit body means, press one time you will get the face. Press again double click on it, you will get the, you will select the entire body, okay? So one time I am selecting the face, right? I am pressing two times, I am getting the entire, I can able to select the entire body. Right click on it, convert, create body into implicit body. This is break, non-design space, okay? Okay, now I will apply the lattice. This is the one I will drag it. Acha, you tell me which lattice I should apply, whether I should apply the graph strut based or 2D lattice or TPMS lattice. In TPMS I will ask you the which one I should apply, and you want to see gyroid, okay, that is TPMS then. So wall TPMS, gyroid squash is there, so this I will increase the thickness, otherwise processing time will increase. 15 I will keep, later we can see. And thickness some 2 mm we can see. Oh sorry, non-design I kept, okay, design I need to keep, okay. So we can increase the thickness. See this is how we can get it, but here the problem is that my attention is to complete the body. I can able to get the design and I can combine this one non-design. Finally I will get this one, but here one problem is there. Can you able to see? Can you able to say? See here. Okay, this is a good thing, and here surface is there. See, suppose if I am applying a bolt, means will it able to fit? There is no threads, right? So that we need to define it as a non-design space. How to define means, this we will see the Boolean intersect, here only it will come actually. So again we will go for the imported body. This one is there, right? This I will select it. These two bodies I will select, whole faces I mean. Those two faces I am selecting, and what I am able to see means I will convert into implicit body. First I told you, right, whatever you want to do the NTOP operation, we need to convert into implicit bodies, okay? First I will convert into implicit bodies and I will thicken the bodies so that you will see that. Control, select the bodies, okay? Convert CAD faces to implicit bodies, okay? See, total 3 bodies are there. See these 3 bodies, okay? So I can apply the thickness to the faces. These are the surface, right? So I will apply the thickness to the surface, okay? Thicken body. So I will drag this. See, the symbol is same, right? I will drag this. I can apply the thickness 5 mm, okay? This is okay? Wait, we will see now. Design, right? Is this okay? Are we getting like this? See, this is the original design. This is the one we are getting, but the hole is not in proper, right? So here is the one we need to apply the intersect. Intersect means common body, it will remove it. It will find the common body, right? So that we can find it, okay? So Boolean intersect. And see, the thing is, this is not even moving. Why it is not even moving means, this is like a two separate bodies, right? So the best way to say this example means, I am deleting this one. Why I will say, see, I will delete this one. I will take this as a single body, and I will do the Boolean union there. Sorry. See, here you can see three bodies are there here. 1, 2, 3. Three faces, three bodies are there. Thicken. Okay. Three bodies are there, but three bodies are not in the same bag. Okay. We need to keep those in the same bag. Then only we can take it into some other place, right? So how to do this means, first I will take the Boolean union. I will delete this one. Because this is as a single body, there is no primary body and secondary bodies. This is as a single body. Those three are separated. We need to take that in the single bag, right? So I will take this and delete it. I will drag this one, so that now this will be in the single body, okay? I mean the shape didn't even change. Now that can take it as a single body. Okay? Like this. Now we can export this one. So this one, and the other one is this one. This one and this one, right? Or otherwise this one we can take it. Okay. This is what is the name of this one? I think design or non-design. Yeah, design means the one we are applying. We are able to tweaking of the design. Okay. So brake pedal, brake design, I think. Okay. See, we are getting right. Now we will see. So is this okay? We can print it, and we can do the threading operation. We can apply the bolt, right? And you can see this is there, right? Why we are getting this bolt head is there, right? It depends the thickness. You can change it actually. If you increase the thickness, the bolt head, it depends on the bolt head thickness also. Like that you can change it. That is bone. No. This is actually that spline curves is there, right? Initially it is there like this. See, this curve is there. According to this line I did actually. This type of operation we can do. Actually that is like a different part. Like SolidWorks we can do. There we can separate the body using the curved path actually. Splines or other we can separate the two bodies. That is I think step file is there. Okay. Actually I did in the I designed in SolidWorks, and I separated this body in the SolidWorks only. There I did actually. So you will get it there, and you can separate it. Bone means STL, right? So we cannot play STL in the SolidWorks. So that's why I prefer the NTOP here. Okay. We can combine these these bodies. Which are the bodies? This one. Why we are applying this one? We are getting the non-design and this one. So we can break underscore non-design 2. Okay. So we can combine these three bodies now. Boolean union. How many bodies are there? So here 2 is there. You can click on the plus. You can import it. Okay. This one, and non-design. Okay. Oh, both non-design applied. Okay. Non-design 2. this one, here this one, yeah this one, sorry. Okay, now we are getting the final design, right? Our holes are, we can preserve the holes and all those things. The main thing is how to identify the design and non, I mean whatever the terminology is same for the both generative and lattice as well as the topology optimization also. The main thing is the preserved region and non-preserved region. Non-preserved means design space and non-design space. These are the non-design space. Always think about it. Holes are the non-design space because that hole has some purpose. We need to put a bolt on it, and we need to do a threading operation. So that should be in the solid format only. That's why we kept it like that. Okay. So that's all from the NTOP. If you have any doubt, you can ask. Otherwise, we can go for the 3D expert is there, that we can go it. Any doubt is there? What's that? Foam. It is there actually. Yeah, it is there. Stochastic means Varna, it is there actually. Varna structure we call it as a. It is there actually, I will show. I mean, I didn't explore all these, I forgot to do all these options actually. Simulation you can do here, I told you right, the simulation structural and these things, static, model, buckling, thermal we can do. Yeah, stochastic you can see here. There Warner surface is there. On the surface also we can like whenever the texture we are saying means that will be applied to the surface only. The term we are using texture means that will be applied to the surface bodies only. That is not applied to the 3D body. Okay. Surface lattice means we can apply the texture. Volume lattice means entire body we can apply. Warner we call it as a. It is there actually. Warner means random points it will apply there is no uniformity actually. That we call it as a Warner. Is this okay? I mean, this is not, I put a lattice actually. You cannot able to get the unit cell. I told you right. Warner means that should be in the random position. From one point to one point it will change actually. So if I want to reduce the size means like this. See, there is no uniformity in this actually. And one more thing is like, I mean it is going beyond, like see here you can see this one, right? The tapered portions is there, right? But that we should not able to get like this. You can see here the tapered portion. We need to get exactly means we can go with the Boolean intersect here. I will show you. It is hanging. can I show this later, like it is system is hanging, because 3D expert is also there, that I will show. Anyway, some people are there, they are interested to know about the NTOP. I will take to the lab and I will show. I will use the same body, so I will combine it. You can save this. Combine. Okay. So, is this visible, right? One more open. Okay. Okay. అదే కావాలి. So we can add the component, and the thing is, this is the 3D expert is the slicing software for the 3D systems machines. 3D we have, since we have a DMP Plex 100 which is supplied by the 3D, you can see the name DMP Plex 100, which is supplied by the 3D system. So they have given the software 3D expert to generate the tool path to put it in the machine, so that we can slice the 3D model. That we can see it now. So we can, same thing, import the component, like in NTOP also same thing. In every slicing software, what are the conditions we are doing means, first we will import the slice, we import it and position the body, and we can generate we can apply the lattice structure, whether any war, like you know about it, right? When can we apply the lattice structure, whether there is any horizontal bridges or overhangs is there. Since lattice is AM is a layer by layer process, we need a lattice what we call support structures, right? So there we need a support structures. So first we need to add the 3D printing component, position it and apply the support structures, and we can give the parameters and we can generate it. We can send it to the machine. Okay, send a G code. Okay, first add a 3D component. I will add this. So I will keep the same position. See here. And has already sir told yesterday about there is some like this is not for all, like as my knowledge I will say, like because you might industry also, like as per my knowledge, for roller support, roller, like this is roller based AM machine. So what will happen, I will tell you. See, suppose this is the thing is there, right? I cannot go there. That is like a straight path, right? Suppose this is the roller is there, and my body is like this. Yeah. My body is like this, and this is the roller, right? Suppose I am applying this one like this, there is a more contact is there. Suppose if I am rotating this one, your roller is there. There is very less contact. I am moving here, less contact. The very starting position, that should be in the less contact actually. Suppose if it is like this, your entire surface is in contact. Like during the very roller is moving like this is the first wave or bill plate. The first part touching is very high contact area is there. So the bill get failure. So what they suggested means they will ask you to rotate the body into 5 or 10 degrees so that the contact can reduce. That is the recommended actually. So we can position the body first. I will apply the support structures here so that you will get to know. Okay. So one I will keep. Delta Z means height actually, like this. Okay. And Z axis I am rotating some 5 degrees. You can change it here 5. Okay. I will be okay with this position. Okay. But there is a problem with it. This is an overhang position. I will show you. See. And why I am applying some particular height to this? Why I need to apply the support? I can print it directly, right? This, that is why. Suppose here I kept it, I have designed with a 10 mm, but your tensile, usually ASTM 8 standard tensile sample will be 2.5 to 3 mm thickness is there. Suppose you have designed with 3 mm, you need exactly powder limitation is there. You need exactly 3 mm output or 2.5 to 3 mm output is there. So for that what we are doing means we are adding a support in between. And if you are adding a support means the SLM, like the support structure means the parameters are different and the like heat accumulation is there, right? That will be more, and we can get a good print if we are applying a support. Be it a solid body or be it anything, we can apply the support some. But here I kept a one body, 1 mm. It is recommended value is 0.3 mm to go for the wire cut TDM. 0.3 mm is enough. Just to apply some different supports I just kept. So support manager I will keep. See, these are the parameters. 30 is there, I can keep it as a 45. Anyway, here no overhang angle is there. So I will keep OK. And this will automatically select the area. You can see here. See, this is automatically select the yellow colored area, right? This will automatically select it actually. So again support manager, see that is the reason we are getting here. See, we are getting the reason, right? So I can apply the support. If I am going with the wire cut TDM means I can apply for the solid support so that I can remove it. But to reduce the post processing time means wire cut TDM, and to reduce the material means I can apply some other material also, like wall type supports and all those things. First I will apply the solid, later we can see the other support. So I can go with the skirt support, that is also solid only. Like in between bases we can apply the skirt support. So I will select this. Solid support. Yeah, skirt here it is there. Okay. Yeah. Since the height is 1, we can tweak this value. I will keep this as 1 since the height is 1, so that we can get the chamfered shape. See, we are getting this chamfered shape, right? Otherwise you can keep with the 2 also, no problem. Like this. We keep this 1. Okay. So this is the one, body, support. You can see here, support, body. Okay. So for the single body we can apply the slicing to reduce the time. So first we can go for the calculate slices, later we can define our own parameters. First we can slice with the default parameter, later we can define our own parameters. So first we will go with the default parameters, click OK, and we are applying a 17.4 pH. You can change the material also, titanium and aluminum, cobalt, chromium, whatever the machine can support. So it will scan the path, and once we have completed this calculated slices, then we can change our parameters as a scan path manager. You can see here, scan path manager is there, means we can manage the scan path. So recalculate slices, and again our intention is to apply the anyway you don't need to work out on the parametric optimization on the supports, right? Because we are removing the support. Our main intention is part, right? So our parametric optimization is on the part. So two types is the part as well as solid support. So our intention is to go for the part. You can see here settings. Yeah. General parameters means layer thickness. We can see here layer thickness 30 mm we are keeping. You can calculate the number of slices. 367 I am getting. And hatching parameters, main thing will come here. Hatching parameters means scanning related parameters like scan speed means laser parameters. Hatching related means hash distance and the scan pattern. These things we can change it. Okay, you can see here this is like a hexagonal. You can see the thumbnail here, rectangular, and if you want to go for the alternative means chessboard actually. Okay, vertical, these things are vertical. Horizontal, something is there, strips is there. I mean here how many scanning strategies are there means strips we can do, rectangular we can do, and rectangular alternative means chessboard we can do, island scan strategy we can do, hexagonal we can do. Okay, again strips, horizontal, vertical, both these things, double centering we can do. And the side step means distance between the hatch spacing. You can see these are the lines is there, right? Each hatch is there. That will go very fast actually. In the during the like printing, you can see the how it is printing. So that is the distance between hatching. Suppose if you want to change this 50 to 45 means we can change it. And strips to, by default it is hexagonal, so I can keep it as a rectangular. Alternated means chessboard it is. Yeah, laser parameters you can change it here. Part right? Yeah, part. 100 watts it is there, you can keep it as a 90 watts also. And 1200 mm layer, these are the default parameters we are using for here. And if you want to keep 600 or 1000, you can do that also here. So if I reduce the scan speed, what will happen? I mean apart from the defects and all those things. More time to scan, right? Right. I mean defects you can forget, like after printing only we can see the defects, but printing time we can see in the software itself, right? That is what. It will take more time. But sometimes we need to compromise on the scan speed also, because optimization is there, right? That we need to compromise also. We need to go for the less speed also to get the better relative dense components. Okay. Defocusing also we can change it, but usually we usually keep that only. We can change it also. That, yeah, variable parameters we cannot keep it here actually. The thing is, the one more thing you can do means you can arrange the like a cards pattern. Cards are there, right? Card house is there, right? Arrange it. You can arrange the two different bodies and you can give the parameters for different. Segments means what is the what if?
Segment, there must be some settings to segment along GI. So that, suppose your part is about 10 mm height and you segment it to 2 mm height. You have 5 different layers with 5 different segments. For each segment you can give different percent.
That is not there here actually. Even though it is there, we didn't explore it much. Maybe in the advanced version it is there. We are using the basic version of 3D Expert. Some parameters we didn't even touch also, because our main intention is to print it, and to get the printed means parametric optimization that should be in the dense component. So that we have completed successfully, and once we get the parameters means we are going for the application point of, like I showed you, right? The brake pedal and hip implant is there, right? Those things we are interested to print it, and we have printed also those things. And the lattice structure, these things we are using. That is what. Actually, the problem with the lattice structure specifically for the PBF I am saying, not SLM, not anything, powder based technologies. the powder get trapped actually. While using the whatever the lattice you printed, the powder get trapped inside. If you see any paper or research paper or something related to lattice structure, PBF technologies, there must be say unmelted powder. Yeah, partially melted or unmelted, uncentered particles, whatever it is. Uncentered particles are get trapped inside it because the,
TPMS you were directly able to print without any changes in the process parameter.
yeah.
And stud based lattice structures were difficult. With surface based you were able to print, but stud based was difficult, I think. What from what you have.
Yeah, we get a difficult in strat base because that thing what will happen means during that time this is like a 3 junctions are there, right? 3 junctions are connecting here so that the multiple formation will be higher here, so that the roller axis error we are getting there actually. So we stopped the strat basis. Anyway, our intention is the TPMS because TPMS has a better property than the strat base. This we have scientifically proved in the we have printed in the FDM lattice. FDM printed we have tested and we have scientifically proved it actually.
But there are some good stud based like octane.
Yeah, octet, yeah.
Much better in terms of stud based lattices compared to
T-
TPMS is how in some applications is good, but octane is also cheaper.
like so I will tell you the example. Suppose if you are taking a same porosity like octet and gyroid or some other TPMS structure with the same porosity, 50% porosity, 50% porosity, I definitely say that, yeah, this is one of my paper also there, like I compared these two. In some properties octet is better, like the same thing actually, octet and gyroid I did. In some properties, and that property is that Young's modulus is there, stiffness is there, right? Octet is better because that is like a stretching dominated. Always remember, like I mean this is like a lattice testing parameters like terminology. Stretching dominated has a better stiffness properties actually compared to bending dominated lattice structures. Yeah, all the TPMS, most of the TPMS are the bending dominated, and for strut based how we are saying stretching and bending dominated means it depends on the Maxwell's number actually. There is some formula is there for to calculate the Maxwell.
Potential you were also facing the same wide and optimal.
Yeah, multiple. So we octet means we have printed very less sizes actually. Mainly BCC we are getting this problem.
So what was the stud diameter that you minimum means what was the minimum feature size that you have gone for this stud based lattice and
That time we kept 1 mm I think.
1 mm?
Yeah, 1 mm or 1 mm.
1000 micrometer. 1 mm is radius or 1 mm is
Radius, or we call it a thickness.
so it
Dia.
is 2 mm diameter. 2 mm diameter.
No, 1 mm dia, 1 mm dia. Sorry, okay, you are saying okay, 1 mm dia. Yeah. Yeah. And we use it to print for the SLM sample, we are not going beyond like 30 mm cube or something, 18 mm or 21 mm or sometimes 15 mm also. But for FDM, we use it to print 50 mm size lattices actually. Because FDM is yeah, we can easily do whatever the things we want. That is what FDM. Yeah. Yeah, why? How we are saying optimization means there should be some parameter output is there, right? Based on the output, we are saying this is a good parameter, right? And there are in journals I am saying, I mean, whatever my knowledge, whatever my like research, like I found that the researchers focusing on the two output parameters. Some people are working on the relative density or porosity, good dense structure they are applying, or otherwise residual stresses is there. If the same parameter is giving the best dense results, but very higher residual stresses means they will leave the parameter. Both the things they are calculating. The same parameter is giving acceptable residual stress means they will go for the higher dense structures. The same parameter they will use for the mechanical properties actually. That is how I did also my research. And no. Yeah, okay. That geometry what we are doing means some cube samples is there, right? While doing the optimization, not only we, like everyone will print the cube samples, cubical samples, 5 by 5 by or 10 by 10 by 5 something, 5 mm height only or 2 mm height something. They will print it
and they will test the relative density using Archimedes principle, and they will do the microstructure and everything. Using the relative density Archimedes principle, they will find the porosity, external porosity. Ah. No, no, no. That you are saying that related to design actually. That solid, lattice, solid, porous. That in terms of design you are comparing. But in terms of printer point of view, I am saying. But first we need to fix the printer optimization parameters, right? That only we are doing. Printer optimize. Once we optimize the parameters, then we can go for the design parameters actually. No, no, no. You are getting confused.
Correct, because thermal gradient in case of the lattice structure will be very much terrible as compared to bulk material. The point is correct, because in bulk solid, when you print, suppose after printing second layer or third layer, there will be enough amount of substrate material to conduct the heat to the basic layer. But in case of the lattice structure, if you suppose print single lattice structure, there might be the chances that under surface you will see some kind of gross formation will be there.
Okay.
Under facing surface.
Even wrappage is also there.
So, on tracking it is right, but currently I think your system is not able to, if you set the process parameter at first, it goes on with the same process parameter, it is not able to change the process parameter on during the process itself, but after unless
Yeah.
part itself is completed, it is going with the same process parameter,
Hmm.
not changing.
Yeah. Because we are going, I told you right, our aim is to focus on the design actually. Design means we have printed the, like we means one of my course scholar is there, he has printed so many lattice structure using the default parameters only. In my case, anyway it is completed, like in my case I did the process parametric optimization using the solid bodies, residual stresses I calculated and solid mechanical properties I calculated. Later once everything I got finalized, later I go with the lattices actually. Lattices and I printed the applications using the lattices actually. That is how I did actually, I carry out actually. But one of my course scholar is there, he is not worrying about the lattice parameter. He just did the parametric optimization and got one parameter, and now he is playing with the design things. Like different structures he is applying and he is testing, and whichever they getting the best results means Young's modulus as well as the, I mean you may, if anyone know the lattice structure testing terminology, there is one term is called plateau stress is there. Plateau stress, energy absorption is there. Energy absorption means toughness. In solid body toughness, there energy absorption. Mainly they are using shoe soles is there, right? There they are using lattice structure, energy absorption, helmets is there, car crashing test is there, right? There we can use the lattice structures. It already Adidas, I think, yeah, Adidas is there. Already they have printed this lattice structure. For aesthetic purpose they did actually. Some shoe soles is there, right? That they have printed. Oh, that okay. Actually, that video got famous. Like even one guy is there. The tech guy is there. He promoted that video like airtight ball. It is actually airtight ball. Volleyball. It is there. I think so, right? They have printed using the SLS. Yeah, airtight ball. They call it as a airtight ball, named as a airtight. Wait, also. I will show that. Yeah, this is the one I think. The volleyball with airtight ball we call it as actually. Sports we can use it. Airtight ball, like the same thing they have printed actually. I mean I got inspired from that only, so I designed this one. Just to see volleyball as well as airtight ball. So okay, we can go for here. So once we fix the parameters, we can say okay, save and close. Okay, okay, again okay. I think for body we have changed the parameter to rectangular, alternated. Okay, this we can see in the slice viewer. Yeah, See, this is here hexagonal is there, right? You can see hexagonal shapes is there. Now again rectangular. For now part got started, right? Rectangular this is. And you can see here alternated lines are there. Here like you have seen the chessboard, right? In chessboard what will happen? Like what we call, whatever the black is there, the surrounding will be always a white, right? Same thing here also there. This line is like this, right? The surrounding line won't be like this. See, perpendicular to this. This one surrounding, black and white chessboard. That's why we call it as a chessboard. It is black and white. Okay, like this. Always perpendicular in that like a hatching pattern will be the perpendicular one. So once we are okay with it, we can send this to print. Anyway, we don't print a single part. We can go with the multiple part. This same type of component is there for your printing also. That time also we can say this thing. We can show you in the build view. FAB3 file, the machine will accept the FAB3 files. So that is the one. Sorry that actually I focused more on the NTOP, so I cannot able to convey more information on this actually. But I will show one more thing that I applied the solid lattice, right? I will show the wall type of supports, how can we apply. That I will show. I will delete this. Delete support, not region. So wall support. See. But the problem here is internally it is not applying. Wall means outer body only, right? So we need to do some other thing that I will show you. Add pattern, so that it will add the pattern. Like this it will add the pattern, right? See. And square grid or something we can see, take it. And distance I will keep 2, so that we can get the more. Square shell. Usually prefer cross line or square grid. Okay, this one. And fragmentation means if you apply the fragmentation, there is some gaps is there, see, so that we can easily break it. Okay, the support we can reduce the post processing time. This is one of the technique, fragmentation. Okay, so we can apply this pattern. Now we can go with the wall support. See, now this is this we are getting, right? But I don't want this to be a single thin wall, so I can keep this as a create solid wall. Okay, but internally this is the thin wall. Okay, outer body it will create the solid wall. Okay, now these type of supports we can easily break with the pilers also. Pilers are some post processing tail. There is no use of wire cut TDM here. Okay, we can use pilers and we can remove it. Again, once whatever if you change the position also, you need to do the slicing again. Okay, so we have already changed we didn't change the position, but we have changed the support type, right? So again we need to do the calculate slices. Again the same thing, the same story will happen. We calculate slices and scanning parameters, again slicing viewer, these things we can happen. But usually we cannot go for the one sample print. We can fill the build actually. Since we have a less memory of the laptop, so I use it to go like this. But there we can see actually. Any doubts till now, like in NTOP or anywhere? And in this also we can do the lattice also. But this is, I prefer the NTOP only. This we cannot able to control actually. They have given just to whoever don't have the NTOP license, right? There may be some useful for them. For that only they have given. But there is no control option here. So I prefer that NTOP is the better one for lattice generation instead of this.
While printing a lattice system, do you provide any kind of support? What kind of support you usually provide?
During at the base or
At the base?
at the base we have printed some solid wall actually. That is some tricky is there, like we found it actually. Extra solid wall we have printed actually. Or otherwise we can create a solid wall like I told you, right? Tensile sample is there. Some 30 mm cube I want to print a lattice. 1 mm thickness I will add some extra base is there. that I can separate the body. During that time my design space is on the 30 mm and that 1 mm space is the non-design space. I will apply the 30 mm lattice here, non-design space I will combine it, I will print it. So the 31 mm will come. In that 1 mm I can cut it. Right?
After that cutting, in order to expose the entire lattice, process that using some band paper which can be used.
If you want like a polishing thing, you can use that, like a polished one. Like the wire cut itself is a good one actually. In the band for band side it is not good, but wire cut we can get it. Correct.
But if you directly go for wire cut, to cut the lattice structure or there is some cross-cutting, the wire can damage that. So wire will, because of discontinuity, it will break.
No, it won't damage. We already tried because that structure is the continuous, right? There is no discontinuity in the structure, right? There is a porous is there, but the wire will pass through the porous only. There is a porous is there, but the structure is the continuous. Like one point is there, it will move like this. I will show you. That TPMS you can see here. The structure is the continuous one, right? I mean this will connect to other body. Don't get confused. This is a two separate body, mean that will connect to other body actually, the side body. Okay. And you can see I told you right. The strut formation we have printed the BCC. The problem with the multiple formation here only BCC you can see. The 4 junction points we are the 4 points we are seeing, right? The 4 points is come in contact with each other. So the specifically they told that for roller based thing be like this, if anything happens that will be a problem actually. So the because of the 4 junction points we are getting a difficulty. In octet we didn't feel like this actually. You can see there, yeah, octet. Because octet is a different thing actually. So because of that only we are getting a problem. So later we go for the TPMS structures, gyroid, split P, diamond, squares also we can do. This thing, that thing you can see, that is TPMS and hexagonal square reentrant of the 2D lattice. Once I play the video, see the hexagonal is not changing because the other direction parameters is same, right? Okay, and the square simple game how it is changing you can see. Okay. That's how we can do. Any questions? Lattice, frankly speaking, since we don't have, like I can't say this, like since we don't have a measurement to calculate the roughness actually, the device we don't have, so but the thing is, it is a very rough surface. Using the post processing we have improved the surface, that we can say, because we have seen because of the powder intact with the lattice, right? We are getting a higher like a rough surface is there, and sandblasting we applied actually. Once we apply the sandblasting we are getting a like I did the like morphology images there, I found it actually. There I said this actually. Using the sandblasting you can that powder intact with this one, right? That we can remove it actually. Sandblasting thing. That is there anyway. Tomorrow, I think day after tomorrow, you will get to see what is and how it will improve the surface roughness. These things, sandblasting, post processing, we can see that. Anything is there? Any questions on NTOP or this one? Anyway, NTOP I took more time because okay. No questions? Thank you. Yeah, we'll meet tomorrow at 9:30 a.m. with C. Channabhat sir. Okay.